here. Good. Thank you for you being here, for you also being here. Here you go. Let's wait for more students to come in. Go. Good. That's the one. Today is the 16th. Okay, let's just summarize quickly what we did so far. I'm going to start sharing the screen here with you. Here you go. So here is your book, okay, your textbook. And we started with chapter 15. Okay, we did simple harmonic motion. We did energy in simple harmonic motion. And there is a special type of harmonic oscillator. We didn't do that, but the ideas that we cover can be applied in a straightforward way. There are some details in there that that you have to know to understand. That is the angular simple harmonic oscillator. Okay, how does it work? You know, this simple harmonic oscillator, this this angular simple harmonic oscillator. This is a very important device in physics. Okay, I'm not going to ask that, but at least I want to expose you to this type of angular simple harmonic oscillator. So what does it consist of? You know, it consists of a string attached to the center, for instance, of a disk. Okay, and then what do? This string can be a wire, a metal wire. We use this type of device, this type of element in devices out there to make angular measurements. You twist this disk and let it go, okay? And then the disk is going to oscillate back and forth, but it's going to oscillate, it's going to rotate, okay? That's going to be a torsional type of force that's going to restore the motion of this disk, and we will oscillate around the equilibrium position. Okay, that's what this is all about. The type of motion is the same, but instead of a force, you're going to have a torque in this case. Okay, so we did the pendulum, right? We did the pendulum. That is the simple pendulum. Looks like the book made a mistake here. This is not a simple pendulum, okay? Because he put a moment of inertia right in here. Yeah, looks like the book made a mistake here. And we go, we covered that. We didn't cover the physical pendulum, but I want you to, we didn't cover the physical pendulum yet, but we're going to cover that in our next virtual lab session. Then we went for damped simple harmonic motion. We did that. Okay. And we also did the forced oscillations as well as forced oscillations and resonance. Okay, so let's summarize it here in our notes. Oops. Yeah. Summary so far. Summary so far. Chapter 15. Yeah. Add a bit. (15.1) simple harmonic motion. Energy simple harmonic motion. Simple harmonic motion. That's also called the torsional pendulum. Okay. 15.3. We, an example of, you don't have to worry about that. Okay. Don't. Let's call it torsional pendulum. Don't have to worry about that. Yeah. That's. Yeah, don't worry about that. Don't worry about this one. If you want to learn your own spare time, that's fine. I'm not going to ask that in the exam. And then you have to worry about damped simple harmonic motion. Okay. SHM, right? Damped simple harmonic motion. And we also covered forced oscillations and resonance. 15.5 oscillations and resonance. And then we start with chapter 16. Okay, here you go. I introduced you to transverse waves, 16.1. If there is transverse wave, that means that also there is another type of wave that we call longitudinal waves. Okay, we're going to cover that soon. Wave speed on a stretched string, we didn't cover yet, but we're going to cover that. Wave speed in a stretched string, we'll cover that. All you have to know is the speed of the wave. We're not going to do the derivation, but I'm going to display the equation for you. We're going to do energy and power of a wave traveling. Okay, 16.3 energy. Energy and power. of a traveling wave. We covered that. The wave equation. We did the wave equation here. And here is the, let's see, wave equation. Here you go. Okay, yeah, here you go. Here's the wave equation. I didn't derive this wave equation, but it's possible to do that. We have a derivation here. I also did a derivation by notes as well. Okay, a little bit lengthy, that's why I didn't want to do that. But what you have to know is this final result. That's not difficult to memorize, right? It's a partial, there is a partial second order partial derivative in space and time. And then you must have a proportionality constant here to make the equation dimensionally correct. Okay, so here we go. Wave equation. Let's go there. 16.4 wave equation. We covered that. What else? Interference of waves. That we're going to do that today as well. Interference of waves. We'll cover. 16.7. So when I mention this type of, when I make this list, so it's the topics for the exam, right? That's gonna be next week. Okay, so standing phasors is a very important interference of waves. Okay, that's supposed to be 5 here. Phasors. If you took physics 38, you already know more or less what phasors is. It's a mathematical technique used to solve some problems. It's applicable not just to AC circuits, right? But also you can use that for waves as well. We'll cover. What else? Standing waves in resonance. That's what we have here. Standing waves and resonance. We'll cover. Okay. So let's concentrate on chapter 16. Let's see if we can finish it. Let's just go quickly to chapter 17. Chapter 17 is what? Speed of sound, traveling, sound waves, interference. Interference applied to sound waves, intensity and sound level, beats, a very important phenomenon, applied not only to sound but to other types of waves as well. Doppler effect and supersonic speeds. There's some really neat simulations that I can show you about supersonic speeds. Okay, but let's concentrate on finishing this chapter 16. And what you have to know about, here you go, wave speed on a stretched string, okay? Remember, there is this genetic equation for the speed of a wave. It applies to any type of wave in any medium, okay? And this genetic equation, I displayed that to you before. Let's see if I can, well, I'm going to just type from scratch. There's a very easy equation to memorize. It's not difficult. Here you go. Speed is the wavelength divided by the period of the wave. Okay. This relation applies to mechanical waves. It applies to electromagnetic waves, gravitational waves, right? Matter waves. Apply to. Now, for specific types of waves, so it is also possible to derive the speed of the wave in terms of the properties of the medium. Properties of the medium. Okay? It's possible to do that. So if you have, let's see if you have an illustration here. Here you go. We usually do a it doesn't look like I have illustration here. No, we don't have. I don't have an illustration here. Let me see. Let me see if the book has this illustration. If it doesn't have, I'll do that from scratch. Okay. Yeah. Yeah, I'll have to do that from scratch. Yeah, let me do that from scratch. Very nice experiment that you make, that we perform in the classroom. Use one like that. Let me erase that. Okay. Let's see here. Yeah, I'm gonna use some of. Here you go. We get a string. Okay, attached to a pole, to a little pole. Pass the string through a pulley. Can you picture that? I'm gonna put my pulley right in here. And why are we passing the strings to this pulley? There's a reason. We pass the string to a pulley, and then at the end of this string, right? For pulley, at the end of the string, we attach a mass. That's the type of experiment that we do to generate waves in a string. Okay, so here you go. Can you picture that? Okay. And then we put it to vibrate. We can, there are vibrators out there that can vibrate points of this string up and down. And then we do that, we generate a wave. Okay. This mass here, it is here for a reason. This mass is here to provide a tension in the string. Okay. So that is this mass. That's the role of this mass is all about. Okay. And this string also has a mass, right? This string has a mass. So not only this string is being subjected to a tension, but it also has some inertia due to the mass of the string itself. And when you generate a wave in this string, the speed of the wave is going to depend on the tension that the string is applied, that the mass applies to the string, and also the mass the linear mass density of the string itself. Okay, so let's write that down. Here you go. So for the case, for the case of a stretched string, okay, if we when we generate a wave in the string, and by the way, the string is going to be, in this case, the string acts as a medium for the wave, okay? The string itself is a medium for the wave. The speed of this wave will be dependent of the following parameters, okay? The tension applied to the string and the mass of the string that is written in terms of its linear mass density. Okay. So the tension, the role of the tension is to provide propulsion for the wave, whereas the mass or linear mass density of the string is a term that encapsulates the inertia of the medium. Okay. Like I said, I'm not going to derive this equation for the speed, but you see the derivation is right in here. I did a similar derivation to, using Newton's second law. Here is the string is being disturbed from its original position. The string itself is subjected to this force. There's an element of the mass, delta L here, and the wave is propagated from the right to the left, okay? Here is the mass of the string itself. This section of the string can be approximated to a section of a small circle. And that section of the small circle is going to be subject to an centripetal acceleration, right? And then when you apply Newton's second law, we end up with this equation for the speed of the string, of the wave, the speed of the wave. So what is tau? Let me write that down here for you. Tau is the tension. So let's write that down here. For this specific medium, the speed of the wave is given by V equal square root. The book used the Greek letter tau. I like to use the letter T for tension, okay? Let's see if I can do that. No, I cannot do that. And here you go. That's the force that propels the wave, right? So the speed of the string is directly proportional to the square root of the tension of the string, but it's also inversely proportional to the square root of the inertia of the string, which is going to be the mass of the string. I'm going to put it between parentheses here, divided by the length. Okay, that's what we call, this term is what we call the linear mass density of the string. Go, and we abbreviate that by the Greek letter. Oh, it didn't do it. Mu. Okay, by the Greek letter mu. Let's see if the thing has units of speed, right? Let's do that. Here you go. Let's do some dimensional analysis here. Yeah. Okay, so here we go. We are going it's gonna be like that. U. Okay, unit of the square root of a force divided by the unit of the square root of a linear mass density. Okay, so what we end up having here is gonna be square root of Newton, right? Divided by the square root of kilogram divided by meter. The thing is, again, the thing is supposed to be meters per second, right? Let's see if we get meters per second. I'm going to put everything under the same square root. Okay. Meter goes upstairs. I don't need this other one again. Newton is what? Kilograms meter per second is square. Okay. And do you see the meter per second there? Here you go. This kilogram cancel out with kilogram. The meter ends up being squared. And we finally get meter per second. Here you go. Okay. So if we want to make a way to propagate faster in a string, we have to increase its tension. The higher the linear mass density of the string, the slower the speed of the wave, okay? So it depends on the properties of the medium. Here is the genetic equation for the speed for any wave, but for particular waves, you're gonna have an equation that's gonna depend on the property of the wave. This speed that you see here is going to be equal to this other equation. So, okay. So we have equations like that, not only for the string, for the wave in a string, in a stretched string, but we also have equations like that for an electromagnetic wave, for instance. You know, it's possible to derive, it's possible to, determine that an electromagnetic wave, the speed of an electromagnetic wave depends on the medium itself. It's going to be, let's see here, square root of epsilon, square root of mu naught, mu, okay? And those parameters, they depend on the characteristic of the medium, whether it's vacuum or it is something else, or glass or plastic, right? If it's vacuum, we write that as being mu naught epsilon naught, right? And just like before, this equation also is going to be equal to lambda over the period, or lambda f as well. That way we'll have a specific wavelength and a specific period of oscillation. Okay, and then there are other types of waves as well. And there are water waves, right? That has their specific equation. There are sound waves that have their specific equation that's related to the properties of the medium, etc. That's what you have to know. For the experiment on waves, we will be using this equation here that you see. Any questions about that? 28 students. So that's what we have about chapter, let's see, good. We covered that, we covered, right? Covered, what else? We covered this one here. Wave equation. We also did the examples, right? We also did examples, wave equation and examples of solutions to the wave equation. We did that. (8:35). Let's take a look how we are doing here with the syllabus before we move forward, right? Let's say here's today. For the lab today, I'm gonna help you out with the concept of confidence level that we didn't have to cover yesterday, that didn't have time to cover yesterday, okay? And then next time, we do a lab on the physical pendulum as well. And then we do a lab on, virtual lab, right, on standing waves. The neat thing about this wave experiment, if you have the proper equipment, is that you can do a total of 12 different experiments on waves. 12, provided, of course, you have the proper equipment, okay? Here we'll be covering only 2. I call standing wave 1 and standing wave 2. And let me take attendance. Attendance roster. Today is the 16th. So, am I missing any messages from you? Okay, no. So here you go. Toby, are you there, Toby? I don't hear anything from Toby. Here you go. Harun, are you there, Harun? Harun active. So, no, Harun is not there either. Musa, are you there? Zachary Blue. I see Zachary listed here.
I'm here.
Okay, thank you. Elena Bosshard. Okay, thank you. Luis Crystal. Let's see. Crystal is here. I don't see Crystal in the list. Brian Spino. Nope. Robert Faust. Thank you, Robert. Pedro Flores.
Yeah, I'm here.
Thank you. Lawrence Flores. I don't see Lawrence here. Daniel Freire.
Here.
Okay. Amalia Gale.
Here, Professor.
Thank you. Tiffany Wong. Good. Tiffany, good. Thank you, Olivia Kroger. I see Olivia Song, but not Olivia Kroger. Daniel Liang. Sarina Lobana. Thank you, Sarina. Anthony Lopez. Good. Chuk Lu.
Here.
Okay. Daisy Mass. I see Dave listed. But if you're talking to me, I can't hear you, Dave. Okay, good. Thank you. Ryan McNeil. Good. Gabriela.
I put it in the chat. Here.
Who is that? Okay. Okay, I don't see Gabriela here. Ryan McNeil. Okay, Alexis Nigret.
Here.
Okay, thank you. Daniel Nwagbo. Dave Nwagbo.
Here.
Thank you. Claire Ottinger.
Here.
Angela Padua. Okay, I don't see Angela. Maria Raju. Maria, no. Jennifer Ramirez. Jennifer, are you there? Yep, thank you. Noah Raymond.
Here, Professor.
Thank you. George Risk. I think it's George is here. He's listed. Hi, George. Okay, I'm gonna put a star just to denote that I can see him in the list, but he's not saying anything. Here goes Shah Safi.
Here.
Good. Next is Natalie Santiago.
Here.
Nathan Silva. Good. Thank you, Nathan. Darnis. Okay, I don't see her listed here. Good. Darnis. Kadi Sobi. Let's see. Okay, never came. Kenny Villagomez.
I'm here, Professor. Good morning.
Good morning. Good. Nolan.
Here.
Next is Mengshu Zhang.
I'm here. Good morning.
Okay, good morning.
Professor,
Yeah. Any questions?
here is George.
George, okay. So George, what's the last name?
Risk, R-I-Z-K.
Risk, right in here. Okay, thank you. Anybody else? Let's see. Thank you. And Olivia Song. Okay, so Olivia. Good. Good morning, Olivia. So we have 27. Okay. Who's trying to come in? Musa, okay. Let's put Musa. So very soon Harun should come as well, right? Here you go. Good. Now we have 29. Good. Let's save that here and now let's talk about the energy and power of a traveling wave. Okay, it's possible to derive the equation for energy and power. And the book does that in a nice way. And so not this one. No, energy and power. Of a traveling wave. Okay, so here we go. Let's take a look right in here. Okay, here you go. Consider your wave, right? Your wave traveling in a string, and this wave has both kinetic energy and potential energy. Think about that. Okay, the speed is along, the kinetic energy of this wave can be thought as the kinetic energy of each mass element of the string. Okay, so think about, we have a small element of mass dm here, and this element of mass dm has a kinetic energy that's going to be given by half dm and the speed that this mass element has in the vertical direction. Okay, so here you go. So kinetic, let's start with the kinetic energy, right? Kinetic energy of an element of mass of a stretched string. Okay, so this kinetic energy, this element of kinetic energy, dk, that's going to be given by what? Half the element of mass, okay, and the velocity of that element of mass. The speed of the velocity in this case will be, but the speed that we are talking about is going to be that speed in the vertical direction. The element of mass is moving in the vertical direction. Okay, and it's the wave that moves in the horizontal direction. So what I'm going to write down here is going to be the y component of this element of mass, which, by the way, we have derived before. All right, so here you go. Let's look at this velocity here that we derived before of that element of mass. It's the dy dt, right? Here you go. The dy dt. The book did, let's see. The book did in a different way. Let's make sure here. Yeah, he considered, let's see here. Let's see how different it is. Yeah. Yeah, I use my equation of the wave as being a cosine. The book did is slightly different, but we end up getting the same result, okay? The book considered the y as being sine of kx minus omega t. But you still end up getting the same result. So let's use my own, my own result. So it can be consistent with is what I have here. You go, put that between parentheses and raise to the second power. Okay, we are gonna get a square here, square here. This v is the velocity of the wave, of the wave. And the negative sign disappears because you are squaring it as well. Okay, don't forget this v that you see here is the speed of the wave. Okay. And then what else do we do? To find the kinetic energy, the overall kinetic energy, we integrate over the length of this wave. Okay, gotta put that like that. The integrating factor here is dm. Okay. The integrating factor here is dm, and we can do those same tricks that we saw in physics 37. Okay, though all those terms here are constants that can be taken out of the integral. Okay, we can integrate over, because it's a string, the element of string can be, because it's a string, we can here write this dm, divide by dx, right? We can write that down in terms of the linear mass density. And there's a little trick that we did in physics 37, right? When we were calculating the moment of inertia of one-dimensional objects. Not just the moment of inertia, but also the center of mass. Okay, and we substitute right in here. Let's see here. Okay. And we take this term out, and we are now left with this integral that we can calculate. Okay. We're integrating dx. Well, this term here is proportional to half. We did something like that before in physics 38. Do you remember? Let's see here. Well, let's do it just, let me just remind you. Suppose that you're taking the integral of something simpler than that. Okay. If you go over if you take the integral over the wavelength of this integral, okay, we can calculate this integral in the following way. Okay, so here you go. Cosine, this cosine of 2kx, right? We use those trigonometric relationships that we learned kx minus sine kx. Okay, and this cosine can also be written as 1 minus sine square, which becomes minus 2 sine square. That's the trick. Okay. We solve for sine square. Here you go, minus 1. We change the sign here. And here you go. One minus cosine of 2x divided by 2. Okay. So that's the idea of that integral. Okay. When everything is said and done, okay, you are going to have a result here that, that's going to look like, let's see here. It's going to look like something like that. Here you go. The kinetic energy is going to be here going to be a sign, right? The V that you saw of the wave is implicit here in this term. Do you see here the mass element, right? So he didn't do the kinetic energy here. Let me see. He only did the element of kinetic energy. If you want to find the whole kinetic energy of the wave, you do what I did, right? But what he's doing here, what he did here is to calculate the power of the wave. Okay, so here you go. If you want to calculate the whole kinetic energy of the wave, you do this integral here. But to find the power alone, what you have to do, the power is going to be given by the energy, the total mechanical energy of the wave, which, by the way, is going to be given by the differential of the total energy of the wave with respect to t, right? Which, by the way, is going to be given by dk dt plus du dt. Okay. Now going back to my decay, the equation for the decay here, right here. Okay. Et, okay. Oh, let's see here. dmdt, yep, gotta divide by dt as well. What we want to find out is the average of the power. The average of the power, okay? Which is going to depend on the average of the part of the equation, right? Part of this result is going to depend on the average of the kinetic energy as well. Let me put here the notation. There you go. No, not this one. The other one here. Average. Yep. Averaging that over time, will involve also this integral of the sine square that will result in a term right in here that's going to be half. That's why we're getting this 1 divided by 4. Okay. Now, what else? Okay, so here you go. Let me just write it down, what I have in there. This average, okay, this average now of the kinetic energy, of the variation of the kinetic energy. And it doesn't matter if it's cosine square or sine square, okay? You're still gonna get half when you take the average of either function. You're still gonna get half when you take the average of either function. And what you have in the average that you end up having here ends up becoming 1/4. Okay, the velocity of the wave is implicit here in this omega. And this mu that you see here comes from the fact that we have a dm there in the equation, right? The dm, we had a dm over dt, right? But then whenever you do the chain rule, you can put dm dt is equal to dm over dx, right? dx dt. And when you do everything, you get this result. So that's just part of your, let's see here, my amplitude. I'm gonna copy. Here you go, amplitude. My amplitude square is this one. I'm using A instead of Y. Okay. I'm going to, here you go. We're gonna have the, let's not forget the 1/4 right in here. That comes from this integral here. We're going to have the mu as well. You know, linear mass density that comes from this term, dm dx, dx dt, and velocity. Here you go, the velocity of the wave. Oops, velocity. Oops. Velocity of the wave, omega square. Okay. So that's what we end up having for the average power, the contribution of the kinetic energy to the average power. This is here. This is the contribution of the kinetic energy to average power, to the average power. Okay. Now it is possible, by the way, I'm not going to do that. It's possible to prove that the contribution of the potential energy to the average power is going to be the same. Don't forget, we're taking the averages here. You know, it's going to be the same value. So if you do here for the potential energy, you also get something like that. So when you sum those two contributions, for the average power, right in here. We get, what did I do here? Oops. Let me see, looks like yeah, okay, here you go. Let me get this one, good. You are gonna get a result that's gonna be, twice this value. Okay, so notice that goes with this average power goes with the square of the amplitude of the wave. Okay, that's what we have for the average power. Okay. We can come up with a sample problem. So let's find out the average power of this wave here. This represents an actual, a real life problem. Okay, so we have a string with this linear mass density, 525 grams per meter. That's half kilogram per meter. So seems to be a very thick string. Okay, we subject that to a tension of 45 newtons. 45 newtons is equivalent to a 4.5 kilogram mass stretching the string, and put it to oscillate at 120 hertz. When we do that, the string vibrates with an amplitude of 8.5 millimeters. Okay, that would be the situation is like that. Here you go. Okay, now let me try to, here you go. I'm going to illustrate this string. It's going to be something like that. Here you go. Okay. Let's see. I'm going to go a little bit lower here. So this string is vibrating with this amplitude. It has that linear mass density, the frequency, and this mass here is going to be around 4.5 kilograms. That's the one that's providing. We have, a device here that makes it vibrate back and forth, or you just pluck the string and start to oscillate. If there is no friction, it's going to keep oscillate for a long time, just like it happens to the string of a guitar. Okay, so the question here is, at what average rate does the wave transport energy? What's the average power, basically, he's asking, right? It's just a matter of straightforward substitution of formula of parameters, right? Of values. So here you go. We use this equation here, example, right? Numerical example. Numerical example, here you go. A is 8.5 millimeters, 8.5 millimeters, which is 8.5 times 10 to minus 3 meters. So the linear mass density is going to be 5 to 5 kilograms per. Always get into the habit of solving your problems with the actual SI units, okay? The tension is 45 newtons. Okay. The frequency is 120 hertz. One, two, three, 4 parameters. Okay, 1, 2, 3, 4 parameters. So what you have to do is substitute right in here. Oh, don't forget it's a string, right? A string. So solution. Find the average power. Solution. This V can be here written as the square root of tau divided by mu. Nope, gotta put that. Okay, this one here, omega, is going to be 2 pi the frequency. Then you can substitute all the numbers in there. Let's see, let's do as much simplification as you can, right? This half is going to cancel out with one of those 2's, right? We're going to have the number 2 here. Pi is going to be squared. The frequency is going to be squared. Pi squared. Like that. This linear density is going to cancel with this other linear density downstairs. It's almost a straightforward substitution because you still have to work out some more details. And no, you go when you replace everything in there, you go. You get approximately 100 watts. Okay. See, they put everything in the SI units. So here you go. You put an approximation there. Okay, that's what we have. Let's see, here you go. We did the wave equation, so we are done with this. Let's go back here. I want to copy what I have here. 9:10 already. We should go for our break, right? So we are done with this part as well. And then, you know, we're gonna go have our break now. When we come back, we start with interference of waves. Okay, so let me see. Someone else came in, right? Toby, are you there? Hi, Toby. Yeah, it looks like Toby's away from the computer. I'm gonna put a star here. Anybody else? Let's see here. 29. Okay. Okay, so let's have our break now. It's 9:11. 10:25 break till 9:25 a.m. Okay. And I talk to you soon. Unless you have any questions, we're gonna go into the break. Any questions? I don't hear anything. Okay, so let's I see you in the next few minutes. Starting again. Good. So any questions so far? Okay, so here we go. We did transverse waves, wave speed and a stretch string, right? That, you know, just memorize, just remember that the speed here is directly proportional to the tension that powers the wave, and inversely proportional to the mass density. Is the square root actually, right? Where the mass density is just a term that's related to the inertia. That's why it's inversely proportional. We did the energy and power, we did the waves last time, but now we are going to do is a very interesting topic, is interference of waves, okay? So what happens, I like to think of interference of waves, is what happens when two different waves collide. That's how I like to frame this problem, to formulate this problem, okay? So we can go to Excel to understand what you're gonna have here. Here you go, wave. Here you go. Here's the case of a wave.
Excuse me, Professor.
Yeah.
I don't
Any
think you're
problem?
sharing your screen.
Oh yeah. Thank you. Here you go. Here you go. Here we have the case of a wave. Let me plot it in a better way. Go. I'm going to copy this guy here. Okay, I'm gonna plot a wave at a given instant of time. So the wave would be like frozen in time. Okay. Okay. Now I'm gonna do like that. I'm gonna do like a sine 2 pi. I'm doing that in Excel. I want to encourage you to do on your own too in Excel, because Excel is very helpful in those moments. Okay, 2 pi over lambda. X is going to be my A2, right? And like I said, I'm doing it in a given instant of time, so I'm not going to put the t term in there. Oops. And I gotta put my wavelength as well. Let's put a wavelength of 1. Here you go. Now we got it. The C2 is going to be a constant. Let me see if I got everything. 2 pi over lambda, which is kx. And, you know, I'm making an instant of time equal to 0, okay? And that's going to be my first wave. Because it's my first wave, I'll label it Y1 subscript. I'm gonna go. And let me put my second wave here, Y2. And I'm going to make the second wave is slightly different from the other. Oh, no, 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 no. That's not how we do it. Here you go. That's going to be my lambda, remember? Lambda. I put everything in meters here. Symbol. I think it's a little bit too much. Let's put 0.2 instead. And then I'm going to come up with my second wave here. And my second wave, let's see. Is going to have a phase term, also a time t equal to 0, but I'm going to put a little of a phase term here. Let's see. Let's put 10 degrees of a phase term. And divide by 360 times 2 pi. That's 10 degrees of phase difference. Good. And that's going to be wave number 2. Okay, insert. That they're so now that the phase term is so small that you can hardly see the difference. Let me put a little bit more than 10 degrees. Let's put 30 degrees instead. Okay. Yeah, I know that the problem must be the wavelength. I don't like it. Let's see how I can make it look better. Let's go to a Q10. But then I'm going to do something else. I'm going to connect the dots. In order to connect the dots, I'll have to let's put 2 meters. We have to choose the numbers properly so we can see the wave better. This one here, so yeah, now it's too close together. Let's see, let's put 10 meters here. Okay, better now. In that other way that we're seeing, you can see the phase is very close, right? Here you go. The waves are a little bit off phase. This one here is the first wave. This one here is the second wave. There's a 30-degree phase difference. Yeah, 30-degree phase difference. Okay. So, and I'm going to write down the equations of those two different waves. Here you go. Let two waves of same wave number, not same wave number, same wavelength and period. If you're going to have same wavelengths and periods, then it's going to have the same speed as well. Okay, so we already came up with when I get here though. Same wavelength, periods, and we're going to start with the simplest wavelengths, same amplitudes, wavelengths, and periods. We start with the simplest problem, then we go for more difficult ones. Okay, so here we go. I'm going to interference of wave right in here. I want to do according to the book. So it's the, yeah, sine. He's using sine. Good. Sine, and it's going to be sine as well. But then there will be a phase right in here. What's going on here? No, let's see. Okay, here you go. Consider those two waves. In that specific example of Excel that I have here, the phi is 30 degrees. Okay. What is interference? Okay, interference is when those two amplitudes sum with each other. Okay. The interference is whenever these two waves add up. Okay, depend on the position in space. They may either reinforce each other, right? Or they can, bring the other down, like around this region here. Here they're reinforcing as well. Okay, let me give another example. Here you go. If the two waves are in phase, 0-degree phase angle, okay, they're going to be exactly superimposed to one another. They're so exactly superimposed that you cannot distinguish one from the other, right? That's because I have a 0 degrees here, and I'm going to do even better. I'm going to vary this phase angle according to this value here, okay? And I'm going to put, and now I can control the phase angle more easily. Here you go. So here you go. Right now you have phase. Here you go, phase angle in degrees. If I put 10 degrees here you go. You start to see the other wave. I put 20 degrees here, you see the other wave. Because the phase angle is positive, this wave seems to be propagating to the left, right? 30 degrees, 40 degrees, and so on, right? But if I put, here you go, a negative angle, you're going to get the impression that this wave is propagating, the second wave is propagating the forward direction. Okay. 50, and so on. Comes to a point, right? Let's put that at 90 degrees. See what's happening here. Comes to a point that there will be parts of this wave here that's going to interfere, that we call destructively, with the other. It's going to subtract from the amplitude of the other. There is a extreme case in which the phase angle is difference between them is 180 degrees, and in this specific position, this wave here cancels completely out because of this other one that will be interfering with it. In this specific case, we have destructive interference, but we can also have constructive interference. How does constructive interference look like? Okay, I'm going to show you here. Okay, I'm going to plot the following. I1 plus Y2. Here you go. 1 plus the, oh no, not this one, it's this one here. 1 plus the other. And then I'm gonna plot those two together, right? Here you go. I'm gonna plot all those three. I don't need that anymore. You are going to see 1, 2, 3 graphs there. Insert. Okay, here you go. At this very moment, those two waves are in phase, and you're getting a constructive interference everywhere along the wave. If the phase keeps on changing, right? You still have interference at some. Okay, here you go. Notice that the amplitude is decreasing here because the waves are getting out of phase. Okay, 50. Depending on the angle, it, you know, let's see what we had that before. You gotta watch for those, for this scale, right? Sometimes the scale changes. It looks like there is the wave increased the amplitude when in reality it didn't increase the amplitude, it decreases. It's just like we change the scale. Okay, so here you go. So you saw constructive interference. What about destructive interference? How does it look like? Here you go. Whenever you have 180 degrees phase out, okay? Here is the resulting interference of the wave. Make sense? Again, constructive interference, destructive interference. The green plot is the resulting wave when you sum them up. Okay? That's how it looks like in a graph. Now let's see how it looks mathematically. Let's see how it looks like mathematically, right? Going back to my, okay, interference is whenever these two waves, the equation is whenever the equation, right? The equations of these two waves are added. The result can be constructive interference, constructive, destructive, or a combination of these two. It all depends on the value of the phase angle. Okay, so let's here go. Let's do it. The resulting wave, I'm gonna put resulting right in here, is going to be y1 plus y2. Or we're doing the simpler case in which the amplitudes are the same, okay? The only thing that's different is the phase angle. Let's here write that by putting some of the parameters in evidence. Oops. We don't need that. What's going on? Here you go, like that. Now the question is, can we put this summation here in a better way that we can visualize this equation better? That's the question here that we can ask. Okay, and the answer is yes, we can do that. Okay, we can do that by using the trigonometric relations that we learned in the past. Okay, there is a nice trick to make this relation look better. And the one that we're going to use is the following. There's a formula, trigonometric formula that we can use. Here you go. I'm gonna put it here, in the generic way. Sine of alpha plus sine of beta that can be written down in the following way: sine twice the sine half of alpha plus beta okay, half of multiplied by the cosine of alpha minus beta. I invite you to do that, to expand this term, to expand this other term, and see if you get in there as well. Okay. So when you make this term equal to alpha and this term here equal to beta, what do you get? So here you go. Alpha and this term here equal to beta. Here you go. Let's see, this is alpha. Am I in good shape, right? Sine of alpha, this one, beta is this one, alpha plus beta, alpha minus beta, alpha minus, okay, we have to put a negative here. Here is alpha plus beta. Yeah, I'll put a negative in there. Let's see what we get. Okay, kx that you have here sums with kx. That's going to become 2x. I can take it out. Then we have minus kvt. With minus kvt, you have minus 2 kvt. Right? Now what about here? Kx subtracts from kx minus kvt subtract from plus kvt. Okay, and we get this relation. Let's see if we can do better there. This 2 can cancel out with the other 2, right? Including this one right in here. Yeah, I'm gonna put go y1 plus y2. I can substitute that here. Cosine of minus the angle is equal to the cosine of the angle. So we can remove this negative sign. Let's see, looks like I'm missing something. Oh yeah, I am missing this half here for the phi, right? So we can, this half cancel out with this 2 and this 2, but it doesn't cancel out here. So you gotta put phi over 2 as well. Okay. We don't need that many parentheses. Okay, and let's not forget, I'm forgetting those terms here. All right, let's see, why did I put AKV here? There's no need for the AKV here, just the A, just the A, right? There's no need for the KV here. Okay, so here go 2A, like that. And that's what you end up having. Okay, so here we have the traveling wave. And by the way, I'm going to write it in a different way. Here we have the traveling wave with a given amplitude. And by the way, here we have a term that modulates the amplitude of the wave. Okay, and if you plot this thing here, let's rewrite our equation in terms of this equation now. You're going to see you're going to have the same behavior. Okay, so here go. Let's go to my y1 plus y2 in a different format. Okay, what's the amplitude that I have? I have amplitude 1, right? So here goes, it's going to be twice the cosine of half the phase, right? Times sine kx. We're doing that at time t equal to 0. Sine 2 pi over lambda times A2. And then we still have a phase term, which is half G divided by 2. Did I do it? Did I write it correctly? Let's see here. G 2 pi half G2. No, yeah, that's right. Phase angle sine 2 pi over lambda times x. Let's see if we got it right. It doesn't look like I got it right. Let's see. Twice half of the phase, cosine of half of the phase, and sine 2 pi over lambda. Yeah. Do I have 2 pi over lambda here? Yeah, 2 pi over lambda. Good. I put, yeah, 2 pi over lambda. Times x, yeah, plus this phase divided by 2. Yeah, there's a problem. For some reason, this one is not coinciding with this one. There might be a mistake here in my calculation. Oh, yeah, must be this one. Let's see, half. That's what we call 2. We didn't quite get it. Let's see here. Okay, it works for phase equal to 0. Okay. Yeah, it's working for phase equal to 0. Here you go. So I wrote the equation in 2 different formats, right? And I'm getting the same result. So one minus the other should be 0. Here you go, this one minus this one here. Right, here you go, 0, 0, 0 for everything. Let's play with the phase. Here you go. This phase here. Let me see what's going on here. Let me get that. Yeah, there might be a little problem here in my equation. Maybe it's a matter of sign. Let me check here. Maybe it's a matter of sign that can be fixed. Let's see if that's the case. No, it's not the case. Well, I cannot figure it out now. But anyway, let me erase that for you. Okay. So I'll look into that next time. But that's how we can, here write the sums of 2 signs with a slightly phase terms a slight with a phase term that we have here. Okay. So that, any questions about that? Let's take a look here at my notes. Standing wave, superposition, interference, superposition of waves. Yeah, that's the one. We go. Backwards, interference. Minus omega t. So let's go back here. So that's the term that's modulating your amplitude. If you have a pi amplitude here, pi over 2 is going to have a cosine equal to 0, right? And everything is going to cancel out. Which other way can we do this type of math? Okay, there's another way to perform this type of math. Is by working with phasors. Okay, is by working with phasors. So how can we represent what is phasors and how can we represent waves in terms of phasors? Okay, so phasor is a type of let's go back here. Phasor is a type of vectors in the space. Here you go. I have one here for you. Okay, let me start. So suppose that we have the x, y, coordinate space, right? Okay. So if we have a wave, and here I'm gonna start from scratch. you know. It is possible, okay, to represent our wave in this XY coordinate axis by a vector like this one here that has a length A. This vector has a length A, and it's also making an angle phi that reflects the phase of the wave. Okay, so here you go. The projection of this vector along the y-axis is what is represented by the wave. At a given x position, we can state that this vector is rotating as time goes by, either counterclockwise or clockwise. In this specific case, because we have a forward propagating wave, this vector is rotating in the clockwise direction. Here you go, like that. Let's see. Match shape. Line right in here. No, you got the other direction, right? Go. Can you picture that? So as time goes by, this angle should decrease because you're subtracting this term here, the ZT term. Okay. If you were a positive sign, this vector should be rotating in the other direction. Now, what about the other vector? Right, here you go. I'm going to copy this one right in here. Okay, and I'm gonna paste it there. I'm going to erase this one for now because I just want to concentrate on the other vector. I don't need this one on the other phasor. Okay. Okay, and because again, because we have this negative value here, this phasor is rotating in the clockwise direction. Because here, I'm gonna even ensure that I put the negative there. I don't need that. I don't need that. Okay. Time t equal to 0, x at a given position. Okay, that's for both vectors. When you sum up, when you consider both vectors, okay, so here you go. I'm gonna get this paste right here. Let me move it away. Okay, I'm gonna make it. I'm not gonna sum the vectors yet. Okay, here you go. Here's the phase angle
of the first wave, right? The phase angle of the second wave is 0. How do I get the resulting wave? We get the resulting wave by summing those two phasors vectorially. Okay, and that what, and let's not forget, here you go, those phasors are rotating with this angular velocity, kVt or omega t, 2 pi over lambda, right? We sum those two vectors. There you go. And we end up here with this resulting vector. Here is a sine kx minus omega t plus 5. This is sine a sine kx minus omega t plus 0. Okay. The resulting vector, the resulting phasor is going to have a different amplitude, A prime, but is also going to have a different phase angle that we call beta. Okay. Now, this at this very instant of time, you know, we have this component here that's a sine of 5. How do we get A prime? Okay, we get A prime by, you know, doing the cosine, the laws of the cosine, using the laws of the cosine, okay? Let's do that. Let's see what we get. Okay. Okay. So this A prime here, right, is going to be what? A square plus A square. And then there will be another cross term that's minus 2A square cosine of beta, right? That's what we have when we use the phasor technique. So what you've seen that for the first, you've been seeing that for the first time, how do we start? Yeah, we start with by looking at each phasor separately. Okay, that's the first one, and that's the second one. If you are summing them, put them together, right? And then you sum those two vectors, those two phasors vectorially. That's your resulting, which ends up being your resulting wave. Okay, that's what we have for this chapter here, for this section. And then we can start talking about standing waves and resonance as well. Okay. Well, standing waves is just a result of interference between vectors. That's what it's all about. That's why we cover standing interference first, okay? So let me, before we go into that, so here go phasors. is a vectorial technique used, used to determine the resulting wave when a resulting wave. So it's a vectorial technique used to determine a resulting wave when two waves intershift. Okay? That's what it is. And now we can start talking about standing waves. So that's this section right here. Well, standing wave is a special type of superposition of waves. Okay. So when you have a string, two ends of the string fixed. Okay, what you're going to have, you're going to have, and then you generate a wave at one of the ends of the string. What you're going to have, you're going to have this wave propagating from my left to the right. And when it reaches the other end of the string, it's going to reflect. Okay, the wave itself is going to reflect. Let me give an example here in my PowerPoint slide. Here you go. Here I am illustrating just a pulse of wave, just a pulse here in the string. Here you go. Not a train of waves, but a pulse only. So the wave started at this point, and then we have this other end of the string that's fixed. Okay, the wave propagates towards the other end, and then what happens? If this end is fixed, the wave is going to reflect, and it will reflect. Not only is going to reflect, but it's going to change amplitude. It's going to change direction of the amplitude. It's going to propagate back. Okay, that's what you have to know about that, about waves. Reflection of waves at the fixed end. If the end is not fixed, you go free end. Start with a pulse, and then we are going to expand this knowledge to a train of waves. So the pulse is going to propagate, and then what's going to happen? Once the energy reaches the other end, it's going to reflect again, but it's not going to invert the amplitude. Okay. Why does it happen? Well, it happens because during the reflection, because this end is free, No, I cannot do that. Okay, I'm gonna erase that one there so you don't see it. Here you go. White. Yeah. That's what was happened to the wave, right? Because this end is free, it's going to move up and down, and then it's going to generate another wave in the other direction. Okay, so here you go. That's how the situation. Oh, no, don't need that. A wave is gonna move a little bit forward. I'm gonna get another one here. right? This is move for that's a very qualitative way of explaining how waves are reflected both at fixed and free ends. And eventually, you know, it reflects back in the other direction, but with the amplitude upright, with the initial amplitude, with the initial direction of the amplitude. Okay, there you go. So now, what about if you have the transmission? So we can have reflection, two types of reflection, fixed end and free end, right? So let's reflection of a wave, no? Fixed end, free end. Wave is reflected upside down, wave reflected upside down. Free end, wave reflected upright. Okay. But you can also have transmission of waves. We're going to use both cases later on. Okay, and then we have two cases, you know, from lighter to heavier media. Oops. From heavier to lighter medium. Okay, so what happens here? Reflected upside down, and some of it is transmitted. Reflected upright, and some of it is also transmitted. So two cases. Let's go here to the. So here you go. Here we have a string, and here we have another string, but we have a heavier string. It's thicker. The wave is propagating from the left to the right. Okay, when it reaches the interface of this medium, what's going to happen? Some of the wave is transmitted and some of the wave is reflected back. Because the medium is heavier, the medium on the right side is heavier, the reflected wave is reflected upside down. Okay, well, what if you have from a heavier to a lighter string? Okay, so we're still going to have transmission. And you're going to have reflection, but the reflection is going to be the wave is reflected with a, you know, it's reflected upright. Okay, I can move forward. Yeah. Oops, here you go, I got it. Those are very qualitative ideas of waves. Okay. Now we're going to use the first half for the case of standing waves. Okay, let's see if I can get a drawing here of a standing wave. Well, yeah, I don't have it, but let's do the follow. It's already 10:20. Let's have our break again, and then we continue with this material. Okay, it's the break. 10:35. Any questions before we go into the break? I'm gonna pause the recording. Okay, and I'll see you soon in 15 minutes. Here you go. I'm back here with you folks. Oh, and then I'm gonna share the screen. Okay. Now we're going to talk about standing waves, which is going to be one of so-called virtual experiments that we're going to do. And what is a standing wave? Huh? A standing wave is the type of wave that you see when you pluck the strings of your guitar. Okay. So in that situation, what do you have? You have a train of waves propagating forward and backwards. Okay, so here you go. And when they propagate back and forward and backwards with the two ends of the string fixed, what's going to happen? You know, the wave that's propagating forward is going to reflect it backwards, right? Because we still have more waves coming from the left side, the wave that is propagating to the forward is going to interfere with the wave that's propagating backwards. Okay, so let's write that down here. Standing waves occurs whenever you have two waves propagating in opposite directions while interfering with each other, okay? A typical example is the wave that you see when you pluck the string of your guitar. The wave is called standing. The wave is called standing because it looks as though it is not moving, when in reality, right, you have two waves, one propagating forward, right? One propagating forward, and the other that was reflected at the fixed end of the string, upside down, moving in the other direction. Yeah. We can model this type of situation as well. Okay, strictly speaking, okay, in the most generic sense speaking the most generic sense, right? You can have, here you go, I'm gonna you can have one backward, forward propagating wave. I'm gonna explicitly, put the F in there, summed up with a backward propagating wave, which is gonna result in a standing wave. A standing wave, we go. Standing wave. And what, that's the most genetic way of expressing here the standing wave. But what we're interested in waves, we're interested in waves that are planar waves. Most planar waves are, let's say, planar waves is a very good approximation for any waves, okay? Here we study planar waves, we study planar waves because because this type of wave, right? This type of wave is a very good approximation for many waves out there. So here we go. So let's write down our forward propagating wave. Okay. And our backward propagating wave. Oh, don't forget to put the amplitude. You go, amplitude right in here. Let's sum those two together. And let's see how it looks like. Here you go. Forward propagating wave, backward propagating wave. See, backward propagating wave, I put a positive sign here. We are going to collect the common terms. All right. Oops, I cut down my sign here. And then what's going to be the next step? Well, the next step is going to be to expand those two terms. Okay, so it's just like sine of A plus B and sine of A minus B. And let's see what we get, right? Okay, that's going to be sine kx, sine kx, cosine minus bt, right? Plus sine of kx, kbt. Let's not forget kbt, which is end up being omega t, sine of minus kbt. Cosine of kx. That's for this term here. Then you gotta do the same for this one. I'm going to Okay. So what's it gonna be? It's gonna be sine kx cosine of kvt. Oh, let's see. Sine of kvt cosine of kx. Okay, so what else can we do here? Let's go to the next step. This negative sign disappear because cosine of minus a is cosine of a. Okay, but this one is going to be negative, right? And then we have those positive terms. Let's see what else can we do about that. This term here, let me copy and paste the next line. This term here cancels out with this term here. And we are left with something simpler. This term is equal to this term, right? So we're going to end up with twice of the remaining terms. And I'm going to rearrange it. Here you go. I'm going to put this term right in here. And then what do we get? You know, I'm gonna write it in a different way. Here you go. I'm going to say that what you end up having here is an amplitude that changes as time goes by. Here you go. And I can remove the dependence on cosine kvt, okay? That's what this term is all about. This amplitude is increasing and decreasing, okay? All the way up to 2a, all the way down to minus 2a, all the way up to 2a. Can you picture that? And the format here remains the same. It's just the amplitude that changes. You still have a sine of kx, but with amplitude that changes back and forth, okay? That's the impression that we end up having. We end up having an impression that the wave is standing. It's not, there's no motion in there in the horizontal direction, the propagation direction. When in reality, there are two waves moving, one in the backward direction, the other in the forward direction. Okay, that's so. Note C that the amplitude of the wave varies from minus 2a to plus 2a. When do we get an amplitude equal to 0? When do we get an amplitude equal to 0? Okay. We get an amplitude equals for the whole wave, right? For every point of the wave, okay? For every point of the wave. Here we get an amplitude of 0 for every point of wave whenever this term is equal to 0. Or cosine kvt equal to 0. Okay, which means kvt equal to what? Pi over 2 over 2, you know, 3 pi over 2, and so on, right? 5 pi over 2. Oops, 5 pi over 2, etc. And so on. At this instant of time, I can even put that 5, 7, right? So what's end up being 2n plus 1 in a genetic sense should be 2n plus 1 for n equal to 0, 1, 2, 3, so on. Okay. Time t, that instant of time t is kv. Let's put here kv. I'm gonna put the kv right in here below this one instead. Okay, let's see if we can do better than that. I see we can, yeah, we can do better than that, right? Because the v can be written down in terms of the wavelengths. So that's the, so is the k 2 pi over lambda. The velocity times the frequency, the velocity wavelength times the frequency. I want to remove this. It stays to be intended that n is a integer. Let's see, we can do better than that. We go pi, cancel out this pi, lambda cancel out this lambda. 1. And 1/4, like that. Okay. For n equal to 0, the first instant of time is going to be 1 divided by 4f. Which also can be rewritten in terms of the velocity and the wavelengths. Remember that the frequency is v divided by lambda. Okay, so I'm going to put it this like that. It's another way of writing the same equation. I think this one is simpler because it involves just one parameter. Here it involves 2 parameters. Let's take a look at one of my standing wave. Okay, here you go. Here is a simulation of a standing wave. Let's see if we can. Here you go. X, Y, and X, right? Time t equal to 0. All points in the standing wave have amplitude 0. So let me see. For some reason, my simulation is not working. Let's see what's going on here. Let's see. We got sound waves, the standing wave. No, not this one. Maybe this one. There's waves. Yeah, every now and then I do not know what happened. Let's see. Here you go. Every now and then, for some reason I do not get it to work well. Let's see, 0, right? Let's try 0.1 maybe. Oh yeah, that's because the time interval has to be very small. That's the reason. Okay, so here you go. Let's start again. 0.01, right? 0.02. Okay, so you gotta be careful how you choose your instant of time. 0.04, right? 0.05 and so on. Okay, I can also animate automatically that, but I'm just being lazy, and because I'm being lazy here, then it takes me a long time to show that to you. Okay, 0.1, here you go. 0.11, 0.12, 0.13. Oh man, 0.14, 0.15. Here you go. 0.16, 0.17, and so on. Right? The amplitude should be 0.2. 0.18. Let's see if it goes any higher than that. 0.19, 0.2, 0.21, and so on. Okay. 0.24, let's see. 0.25. Very soon you should start to go down. Let me see. 0.3. Let's see. 0.3. Yeah, here you go. 0.3. 0.31, and so on. That's the type of motion that you get, and that is for the what we call a fundamental mode. That's the type of vibration that we see in the string of a guitar, right? We play the string of the guitar, and you see just a single row being there. We can, so this guy is going to oscillate back and forth. Okay. Notice that the wavelength is 100 units. Should be centimeter because I put in centimeters here. But the lobe itself has half this length, half of the wavelength because of the type of wave. Okay. What about if the wavelength is 50, right? Now we're going to have two lobes for this specific case. What if the wavelength, let's say 25, is going to have 4 lobes? Anywhere in between that is going to be 50, 75 divided by 2. Let's see if we get 3 lobes. Yeah, no, we don't get 3 lobes. It's not 37, 75. Yeah, it's another number. It's not that. Okay. But we can calculate that. Let's go back to 100 here. We can calculate what that is. Let's see how we calculate that. Okay. So when we have so suppose that this type of wave has very simple relationships, okay? So consider a standing wave propagating in a string of length L. Okay. Okay, so here we go. What we have different types of, we have different types of standing waves. Okay, so let me see, we have an illustration here. We have different types of illustration. Oh, not this one, let's see here. Okay, here you go. That's what I want to show you. This is what we call the fundamental mode. Okay. In this fundamental mode, just like you saw before, only half of a wavelength fit between those two fixed ends of the string. So the length of the string is going to be equal to half of wavelengths. Let's write that down. Here you go. The standing wave, that is the fundamental mode, right? Fundamental mode has the following relation. Okay, so here we go. A full length of the wave is going to be equal to a half wavelength. Okay, and then we can have another one too as well. The next one is going to be, only certain wavelengths fit here. Only waves of certain wavelengths can fit here. You cannot have a wave of, let's say, a quarter of wavelengths propagating here in this string. Okay, so the next one will be a wavelength that has the length of the string itself. Okay, the next standing wave has the following mode propagating along it. I'm gonna fit it. Something like that. Here you go. And then, so the way it goes is like that. Half of wavelengths, 2 wavelengths and a half, 3 wavelengths and a half, 4 wavelengths and a half, and so on. Can you memorize that? Simple, right? Half, 2.5, 3.5, 4.5, 5.5, and so on. All right. So I'm gonna be very explicit. 2.5. It's gonna be like that. You go. 1.5. 3.5. 4.5, and so on. In other words, the wavelength that you're going to end up having propagating in this wave is going to be has a generic equation. It's like that. You go. And lambda, I'm going to put lambda sub n, because those are going to be different values of the wavelength. No, for n equal to 1, 2, 3, blah, blah. Okay. That's the equation that we get for the values of the wavelengths that are restricted in there. Okay, so let's see now. Okay. And I can here write in terms of the wavelengths. The wavelengths in terms of the lengths is going to be 2L over N. That's another way of looking at that equation. Okay. 1, 2, 3. So now let's see if that works there in my equation, right? Here we go. L over N. That's my L. Okay. 12 over N is 100 for N equal to 1. For N equal to 2 is, oh, no, I put it the wrong one. Here you go. N equal to 2, right? It's 50 here. N equal to 3 is 2/3 times 50. Let's see, 2/3 times 50. Let's see if we get it. Yeah, now we got it, right? 2/3 times 50. 2/4 times 50. Now we have a standing wave there. This one, 2/5 times 50. And so on. 1, 2, 3, 4, 5. 5 lobes. And so on. Okay. Yeah, next one should be 2/6 times 50. Here you go. Yeah, 1, 2, 3, 4, 5, 6 lobes. Works well. Okay. This point here is called a node. That's another node, right? How do we find the position of the nodes? Go back to our equation. Do you find the x coordinate? The nodes. All right, so go back to our equation right here. Here you go. Okay, nodes are places when this equation ends up being equal to 0. For a of t different of 0, we are going to find the nodes whenever sine of kx is equal to 0. All right? And sine of kx is going to be equal to 0 whenever kx is equal to 0, pi, 2 pi 3 pi, 3 pi, etc. etc. Let's here is going to be, nodes. I'm going to put it nodes, x nodes, right? X of the nodes. X of the nodes. So I'm going to write down an integer. I'm going to put capital N so we can distinguish from the other lowercase. And capital N is equal 1, 2, 1, 2, 3, right? Like that. X node, capital N, pi over k. And here's 2 pi. 2 pi over lambda. Okay, one more step. Pi cancel out this pi. It's going to be like that. So x nodes. I'm going to just repeat this equation, but in a more organized fashion. Okay. So going back here, integer divided by 2 lambda, right? Let's see. We have lambda here, right? So half lambda, right? 1 half lambda, 2 half lambda, 3 half lambda. That's a lambda. That's a wavelength. So here's 3 half lambda, 4 half lambda, right? 5 half, 6 half lambda, and so on. So that's the boundary condition for x equal to 0. And for x equal to 0 and x equal to L, right? And y equal to 0, right? Y equal to 0. All those points is for y equal to 0. We have 15 more minutes. Any questions about that? Here you go. Let's see if we get some interaction going on. See, we have 27 students here. Yeah. Okay. Note see that going back to our notes. Note see that when we found the equation for a standing wave, we sum up waves of positive amplitudes. But if that wave, the backward wave, is being reflected upside down, so we could repeat this. This wave would be instead minus a, right? Well, we will get a similar result. It's just a difference in the phase. Okay, you can repeat that on your own. Here you go. Now consider. Now consider the following two waves interfering with each other, right? Repeat what I want you to do there on your own. Repeat what we did above. Repeat what we did above for these two waves instead. Okay. We're going to have something similar, but with a different phase angle. Okay. I will let you do that on your own. 15 minutes more to go. So here you go. And that's what we have. We're working on transverse waves. So this is a transverse standing wave. That's what we did. And why is transverse? Okay, it's transverse because the displacement is transverse to the direction of propagation of the wave. Okay, let's see. And yeah, here you go. That's the direction of propagation of the wave, but it is transverse because those points move back and forth, up and down, not back and forth, but up and down. All right, so let's do that again. Here you go. Let's see if it works. 1, yeah. 2, right? Oh, yeah, you should monitor this one of these points. Let's start again. You're gonna put a t equal to 0 and data label. Marker, that's what I want. I want to increase the size of this marker so you can stand out over the other, right? Here you go. Here's my marker. No, I don't want to increase this marker. I want to increase the other one, another one here. Here you go. Increase this one here in the middle. Here you go. Let's keep track of this marker as the wave propagates, right? This point is going to move as though it is a simple harmonic oscillator. Okay, so here you go. Watch this one. Here you go. 1 second. Oh, it's too much. It's too much. Let's do half of a second. Yeah, better, right? What about 0.2 seconds instead? Let's do 0.2 seconds. So you can, you go, yeah, better now, right? 0.4, 0.6. See, this point is going to move as though as it is a simple harmonic oscillator. Okay, 1.4 and so on. In the transversal direction, this point is moving up and down, transversal to the propagation of the wave, 2 different speeds. The speed of the points, of the physical points of the string, and the speed of the wave, which is something that doesn't have mass. The wave itself doesn't have a mass. It's just propagation of energy along the medium. Okay. Again, that's for transversal waves. What about longitudinal waves? Okay, all the above was done for a transverse, not just for transverse standing wave, but for any transverse wave. Okay, what about a longitudinal wave? Longitudinal wave. What about a longitudinal wave? Okay. Here you go. Transverse wave. Looks just like that. Longitudinal wave is a little bit trickier than that. Okay. Okay, in the case of a longitudinal wave, I have a simulation here. for the case of longitudinal wave, what each point in the longitudinal wave, I'll call it S, is oscillating back and forth with a maximum amplitude. Oh, what's going on here? Okay, better, max, okay. Given by something like that as well. The difference is that oscillation occurs in the same direction as the direction of propagation of the wave, okay? While you have one of the points oscillating back and forth along the x-axis, for instance, you visualize, you see a wave moving past this point, okay? It's more like an optical illusion. Then it's not exactly, it appears to be an optical illusion, but it's not, because you do have energy propagating along there. Okay. Let me show you a simulation of that. Here we go. Standing waves, sound waves. Let's see here, this one. In the case of sound waves, for instance, sound is a type of longitudinal wave. That's what you have to know. And then what's happening? Again, I'm going to get one of those points here and make, no, it's not what I want. That's the line. Data point, is that the one? Let's see, marker. Yeah, I'm going to increase the size of my marker. Each of those points are oscillating in the direction, in the horizontal direction. Okay. Here is a very good model of how a sound wave behaves. Each of those points is a molecule of air. Represents a molecule of air. Okay. The higher the concentration of those molecules, the higher the pressure in this region. Okay, and that's how you end up hearing sounds, is a difference in pressure. Okay, we're not talking about sending waves yet. Okay, so we're just talking about longitudinal waves in general. So here you go, let's start at that time t equal to 0, right? Let's see, one. Too much, right? Too much. Gotta learn. Here you go. Looks like it's too much as well. Let's see here. Lambda v. Let's see, 0.1. Let's try 0. Okay, good. It's a forward propagating wave. 0.2. See? 0.3. Okay. And each of those points is oscillating about a point of equilibrium, like this one here. 0.3, 0.4, okay, 0.5. See that? That point? 0.6. Let's see here. 0.7. Right? 0.8. Yeah. Now my point is going back to its position of equilibrium, right? 1, watch it. Yeah. It has a little bit of a higher amplitude, 1.1, 1.2. Now it's going back. See that? But the wave is propagating to the right. But each of those points are seen. Not that they are seen. Each of those points, they oscillate about a position of equilibrium. 1.5, 1.6. Here you go. 1.7, 1.8, 1.9. Here you go. 2, right? 2.1. Did you get the idea how we can get a longitudinal wave? So in the case of longitudinal wave, we have a collection of points, just like we have a collection of points in the string, along the string. But in the case of the string, it oscillates up and down. In the case of longitudinal wave, it oscillates in the direction of propagation of the wave, in the horizontal direction. I hope you can get a good picture of a longitudinal wave. Okay. And let's see, let's take a look at the stand. Okay, here you go. Here's the case of the standing wave now. In the case of this standing wave, we have a similar situation. We have, here you go, going back to the sound wave here. Here we have a forward propagating wave, right? Here you go. Here's the equation for my for the points in the forward propagating wave. Okay. Kx, write down the equation. Do you see the minus sign here? Means that you get a forward propagating wave, right? If I put a negative sign here in my velocity, you're going to have the impression that this wave is propagating to the left. 0.1, 0.2, 0.3, 0.4, 0.6, 0.7, see that? So everything was done properly there. But this point is still oscillating back and forth. It is as though as this wave is kind of an illusion of the mind, but it's not exactly an illusion because it does carry, like I said before, it does carry energy along with it. Let me go back to what I had before. Here we go. Okay, so good. So let's run the movie again. Here you go. See the point now. The point is oscillating, but the wave is going by. It looks like this point is oscillating somewhere around here. Okay. So I had a point at y, a set of points at y equal to 0, right? You see that? I put the x coordinates from x from 0 to what? From 0 to 5. From 0, okay, to 10. From 0 to 10. Okay, here you go. 0 to 10. And then I did for several values of y at 0, y at 0.1, 0.2, 0.3, okay, and 0.4. So I have only 5 rows of those points which are oscillating around a position of equilibrium. Let me see, someone has the graph. Oh, thank you, Sha. Yeah, it was lots of work to do something like that, but it was fun. It was fun. You might want to try to do that yourself too. Maybe it's gonna take you like 3 hours to do that. I don't remember how long it took me to do that, but yeah, I'm very proud of those graphs. And in the process, I learned too. Okay, so yeah, if you do that, you're gonna learn things that you don't pick up right now. Okay, but here's the equation. Let's see. What about the standing wave? Not this one. I have a standing sound wave somewhere. Let me see. Standing. Okay, this one, right? And now this one, what's that? This one is a forward propagating wave. This is forward because we have a negative sign here, plus a backward propagating wave. It's a backward propagating wave because I have positive sign here. Okay. So let's see how it looks like. You know, Excel is a very powerful tool, okay? We can even plot three-dimensional graphs with Excel. And it's so powerful that I use it in my own research. So let's see if we can get a standing wave, a standing longitudinal wave. And just like before, I'm going to oh, it's 11:30 already, right? Let's see, let's go a few more minutes. Let's go until 11:35 and then we meet at 12:05, right? And change data format points, marker. Here you go. Increase the size. I'm increasing the size of one of the points so you can visualize that it's oscillating back and forth, right? That's the only reason I'm doing that. And why is this thing appearing here? It's not supposed. Let's see what's going on. Huh, interesting. Let's try it again. Sometimes Excel does something that I myself don't understand, you know, and you just have to revert it and do it again and hopefully and hope that it's not go back. Here you go. Here you go. Oh, you see, why this guy is showing up? I don't know why it's showing up. Nope, no, we don't want to do that. Shouldn't be showing up. Might be one of the options there. Let's see, select data, change series, add format data point. When I format the data point, the values for some reason shows up. I do not know why. Marker option, is that in the marker option? Let's see. Okay. No, oh, keep on going back, I don't know why. How disappointing. Let me put a little bit aside. Maybe I can even shrink it in size. Yeah, if I can shrink in size, it's not gonna bother us, right? Later on, I'll figure out why it's doing something like that. Okay, so here you go, one of the points, right? Maybe I can even go to from -2 to 2, right? -2 to 2. Can I get that? Yeah. Good. Yeah. So T, let's see. That's too much, right? That's good, 0.1. Let's see here. It looks like 0.1 is too much too. 0.2. Oh yeah, let's start with 0. And then we're gonna play the movie, right? 1. Yeah, that's good. 0.1 is too little. 0.3. Okay. 0.5. Yeah. 0.7. 0.9. I have a macro there that plays those things automatically, but right now I don't remember how to do that, so I'd rather not spend my time doing that with you. Here you go. 1, 1.2, 1.4, 1.6, 1.8, 2, right? So now let's go and do it. Here you go. 1, 2, 3. Here you go. Regions of rarefaction and okay, regions of high pressure and rarefaction. That's what sound is all about. Okay. The point is moving to the left now, is oscillating. Okay, I run out of values here. So it's 11:34 right now. Just that's all I want to show you. And let's meet now at 12:05 for the lab, right? We are going to work on the confidence level so you can do your lab report. And we will meet again next week on Monday after the lab, right? We will first meet at the lab, 12:05, and we work on the confidence level so you can understand how it works. And next week we meet again. So I talk to you soon, in half an hour. Okay. You're welcome. Stop sharing. Okay, we're back here. So what we are going to do today, let me show you the syllabus here. Start sharing the screen. Okay, we are at this point in time here, 16th of June. Have already seen that before, right? We did the first 2 chapters on waves. We did our first lab, virtual lab yesterday. And, you know, I usually like to reserve the following activity to, you know, to help you out with that parameter on confidence level that you saw yesterday. Okay, we didn't have time to go through that yesterday, so I am reserving that today to help you out with that. I like to use this, you know, these are parameter confidence level that's very few people are aware of. We learn this thing in courses of statistics, and it's going, you know, I'm going to explain to you what exactly it is. Okay, so let's go get the notes for the lab notes right in here. P39. Today is the 16th. What I'm gonna do here? Okay, I'm gonna do the following. That was 15 yesterday, right? 22. Today is the 16th. Insert page break. Okay. So, and you should expect, like I said, you should expect a question, one question on the confidence level in the exam. I'm gonna put one in there, maybe another one about the lab, maybe 2, you know, 2 questions out of 20, 10%. So you have those notes here to help you out. So let's see. Let's talk about the confidence level. Call it CL. In order, note that in the table. for the lab, right? In the spreadsheet table for the lab, you have 2 cells that you must write, the CL max and the CL min. Okay. CL max and CL min is not a good name for that. I would should change that. I shouldn't say that CL max and CL min. Instead, I should call them, you know, upper bound, you know, upper bound. Let's see. I'm gonna write that down here. CL max should be interpreted as the upper bound of your CL, okay, of your real CL, as read from the table I'm going to provide you. And by the way, this table is already there in the upper bound, CL max and CL max slash CL min should be interpreted as the upper bound, lower bound of your real CL as read from the table I'm going to provide you. Okay, let's go to the share folder. Use the link that I provided. Hopefully you already downloaded it, but let's see if you have downloaded or not. Here it goes. Google Drive. Go to Drive. Share folder right in here. Go to that link. At this very moment in this link, you have 4 documents in there. The notes the lab notes as of yesterday. The syllabus. Oh, that's the version 2 of the syllabus. Huh? Doesn't look like I have the most updated one. Yeah, I don't have the most updated one. The most updated one is in the Canvas. Let's get it, but let me get the most updated one anyway. So we keep it in 2 different places so you can access those documents more easily. Here you go. We don't need that anymore, so let's remove it. Okay, that's the table that you want to download. Please download the table confidence level.pdf from to download table confidence level.pdf. You're going to need this table for the rest of the semester and even also for your exam, right? Because there will be 2 lab questions there. And I want you to learn how to use this table. It's apparently that's not an easy way to, and it's not something easy to learn, because many of my students are still even though they have been going through my course several times, they still haven't learned how to read this table. It's just a matter of learning how to read the table, okay? And I am going to download this table. Please download yours as well. I'm gonna put it in a place that's easy to find it. Whoa, lots of things. Here we go. Syllabus. Summer. Let's see. Here's the lab. Lab notes. Thank you. Here we go. Oh, always make this mistake. Here you go. Confidence level. Everybody has it? Everybody has the table? So give me some feedback here before we start to move forward. Type there in the chat box, please, if you have the table.
Professor, is there any way you can send the link to the shared folder again?
Yeah, let me get that for you. Don't forget to keep this link in a safe place so you can access it very quickly. Copy link, right? Everyone in the meeting, here you go. So who else? Who else has the table? Let's go through the attendance, right? And then I'll ask whether you got it. No, thank you. Okay, Nolan got it. 16. Jumai, are you there, Jumai? Okay. Brian Spino, are you there, Brian? No, I don't see it. Lawrence Flores. Are you there, Lawrence? I don't see Lawrence either. Gabriela Montes. Angela Padua. Angela Padua. No, I don't see Angela there. Let's see, Maria Raju. Maria. Nope, I don't see Maria. Toby, are you there, Toby?
Yeah, I'm here.
Okay, thank you. Next is Pedro Flores. Pedro, are you there?
Yeah, I'm here.
Okay, good. So Kenny Villagomez.
Yeah, I'm here. I'm here.
Okay, good. Thank you.
Yeah.
And next, Nolan is here, right? Nolan.
Yeah, I'm here.
So Harun Atif.
Here.
Thank you, Musa. I can't hear you, Musa. Your mic is on, but I can't hear you. Good, thank you. Daniel Nuagbo.
Yeah.
Okay, so the question is, have you got the confidence level table, CL table? Here you go. That's the question for everyone here. Table. Toby, did you get your the table?
I'm looking for it right now. It's in the, what's it called? The Google Drive, right?
The Google Drive, I shared the link with everybody right now. You should have the link there in the chat box.
Okay.
Okay, and the table is, here you go, the confidence level here.
Okay.
Okay. So let's go one by one here. Okay, well, mark that you have. Pedro, did you get the table, Pedro?
Yeah, of course.
Okay, good. Kenny,
Yeah, I have it, Professor.
thank you. Nolan, you have the table, right, Nolan?
Yeah, I have it.
Good. Harun?
Yeah.
Okay, Musa? If Harun has, Musa must have too, right?
Yeah.
Okay, good. Daniel, did you get the table?
Yeah.
Good. I will. David Nwagbo, you have the table as well?
Present, I got it, yeah.
Okay, thank you. Zachary Blue, are you there?
Yes, I have the table.
Good, thank you. Elena, have the table?
Yeah, I have the table.
Good. Luis Crystal. Crystal here? I don't see Crystal. Okay, and David Mass. Is he here? Okay, I see David here. I need to hear from you. Either type that in the chat box. Okay, if you don't say anything, I'm gonna mark a star here, Dave. You have that? Okay, good. You have the table, right? Good. Thank you. Okay, next, Robert Faust. Have the table, right, Robert? Let's see, is Dave Robert here? Yeah, I see Robert here. Okay, good. Thank you. Next, Daniel Freire.
Yes.
Good. Olivia Kruger. Good. Chuck Lou.
Yeah, I have it.
Good. Next is Amalia Gale.
Here, Professor.
You have it?
I have the chart, yes.
Okay, good. Tiffany Wang. Good. Oops, one. Yes. Anthony Lopez.
Yeah, I have the table.
Good. Shah Safi.
Yes, I have the table.
Daniel Liang. Good. You have it. George Risk.
Yes, I have it.
Okay. Ryan McNeil. Claire Ottinger. Jennifer Ramirez. Noah Raymond.
I got the table.
Good. Natalie Santiago.
Yes.
Good. Mengshu Zhang. Okay. Next is Nathan Silva. Good, Nathan, thank you. Darnis Simon. Darnis or Darnis, huh? Sorry, I missed your earlier question. I have the second graph. Okay. The question is if you have the table, Mengshu, the confidence level table, okay? You need to download it. You need to download the confidence level table, CL table. Let me show you. You gotta go to the share folder, and you download this table here, this PDF document. Make sense? Right? Okay, so let's continue here. Let's see. I don't see her here. Danis Simon not here. Okay. Kadi. Sobi. No, not here. And next is Aiden. And Aiden never showed up, right? Sandra Valencia. Sandra. Nope. Robert Wall. Robert False, but no Robert Wall. And Olivia Song. Yes, you have the table. Good. Sarina Lobana. Yeah. And Alexis Nigret. Okay, good. So let's see if I have group 8. Now let's see. I'm going to insert. Were you able to register already, Olivia? Olivia, let's see, Olivia. Let's see which Olivia. Oh yeah, Olivia Song. Were you able to formally have?
No, I'm still on the wait list.
Oh, you're still on the wait list.
Yes.
Okay, so stay after the class so I can give you. It looks like you're gonna need an ad code. Okay, the other students didn't need an ad code, right? But it looks like you're gonna need one, right? Sarina, you are able to get into the class without an ad code, right? Okay, and Alexis too, right?
Yes.
Okay. Yeah, okay, so it looks like you're gonna need an ad code. Okay, Olivia, stay after the meeting, and then I will provide you with an ad code. What about Key? Key sent me an email before the semester, but doesn't show up yet, huh? Okay, so let's go through that table. It's just a matter of learning how to read that table. That's how. Okay, once you get the hang for it, you will be able to do all your lab reports in a very successful fashion. And I find that even going through this exercise, some students still don't quite either they don't learn or they don't spend enough time to do it to read the CL in a proper way. Okay, so let's go here. Let me close this one, close this one, close this one. I'm going to need the confidence level table. Here you go. Okay, at this point in time, and I'm also going to open your data, lab one. Let's see. At this point in time, lab notes. Today is the 16th. She goes 16. At this point in time, you already know how to do the following, right? One, plot the graph, right? Insert a trend line. That's what we did yesterday. Display the regression equation, a regression equation, and display the R squared, which is also called the determination coefficient. Okay. Now the next in line here is the CL, or confidence level. Before we get into the confidence level, let's make sure you understand everything else. What is all? You go trend line. What's the trend line? The trend line is the best fit of linear, the best fit, let's see, of an equation, right? For the data you have. In general, we fit a linear equation for the data, in general. But sometimes, it requires more than the linear fit. It requires other types of regression equation, other types of regression equation. Okay, but in general, we use a linear equation. Okay, this regression equation and this, and this regression equation is, in a graphical sense, is the trend line, right? The trend here, the trend line. Let's write it down. The trend line is mathematically documented as an equation, as an equation that we call the regression equation. Okay? There are, statistical techniques to calculate, to determine this regression equation. It's possible, this regression equation. Basically, what we do to get the regression equation. I'm going to tell very broad strokes here. Okay, I'm not going to do this step by step, but given given a set of points, of data points of your graph, y, x. Even better, I'm going to call it y sub I and x sub I, and so what y I x I, no, it should be all the way around, right? Should be all the way around. Here you go. First the x and then the y. Okay. So if we go to one of the data here, that we have here, here you go. Here's the L, and let's say here's the T average, right? Here's your xi, x1, I would say. Here's your x2, x3. Make sense? x4. Okay. Here's your y1, y2, y3, y4. Those are the y values for your first graph. This is the y and x values of your second graph, right? y1, y2, y3, and so on. And here's the y and x values for your third graph. Okay. So given a set of data points, xi, yi, okay, it is possible to obtain an equation, a mathematical equation. Let's say, if it's the case of a linear equation, it's going to be ax plus b, right? In this case, they're not, you don't have a subscript in there. Okay, it is possible, okay, by minimizing the difference y minus yi, the square of this difference. So that's the basic principle of determining your regression equation. Okay. Now that you almost know, okay, because you have taken labs before, your professor must have covered that for you. Okay. And in the process of determining this equation, there is this coefficient, there is this coefficient that we call the determination coefficient. That is a measure of how close your equation is to your data points. Okay, so here you go. This value, I'll say, is a partial measure. It's a partial because it's not a complete measure of how close your regression equation, and I'm going to call it the model, your mathematical model, is to your data points. Your data points are called real life. That's what scientists and engineers do. They try to come up with a mathematical model that is as close as possible to real life, so we can make predictions, future predictions. All right. So that's the whole idea of statistics. Okay. But like I said, you know, R square is our first step in determining how close your regression equation is to your data point. But that's why I said a partial measure. You know, your first step. You know, if R square is equal to 1, right? What does it mean R square is equal to 1? Anybody would like to volunteer here? What means that R is square equal to 1? I already gave you an example, right? What R square is equal to 1. Let's see, someone answer there. If you have an R square equal, it's a 1% of the data is described by the trend line, yeah? Is a what we call, you know, a perfect fit. Yeah, that's right. That's right. Boy, it can be more than one, can be more than one explanation, right? It's either 100% perfect fit to your data point. The trend line is 100% perfect fit to your data points. Okay, another way to explain that, maybe you cheated in the data points just to impress your professor. Look, professor, I got 100% perfect fit. Okay, that's a possibility. Or another possibility too that I have seen before is not that you cheated, nor that you really got a perfect fit, but the equipment that you used, doesn't have enough resolution to do your experiment. I have seen that. Okay, if you're using, for instance, a ruler with a centimeter resolution instead of a millimeter resolution, you may end up getting an R squared that's equal to 1. Okay, it's possible. Something like that is possible. They didn't cheat. They just were not using the proper equipment. So if you get R squared equal to 1, you should start suspecting your equipment. In case you didn't cheat, right? In case you didn't cheat, you should start suspecting your equipment, and you should start considering buying an instrument that has a higher resolution to perform your experiment. Okay, that's a good way of judge what you have there in your as a data. That's what, you know, 100%. R squared equal to 1 means 100% confidence level. Okay, I would say confidence level of your regression equation. That's what it means. It is a measure of how close your regression equation is to your data points. It is a measure of how close your mathematical model is to real life, but it is a partial measure. It's not everything. It doesn't tell you everything. Okay, in order for you to know how good your data is, you know, in order to find out, and that's you know, and that's a mistake that some professors make. Okay, they look at the R square, they get a good R square, and they say, you know, I got R square of 0.9. It means that you know, my data is good within 90%. No. It's not your data is good within 90%. Your regression equation is good within 9%, 90% compared to your data. No. In order to make a statement like that, no, in order to make a final statement of how close your data is to your, not your close your data, how close your regression equation is to your data, you need something else. You need an R square, yeah? Yes, you need the R square plus the number of data points that I put there in the table and data points in your graph. Let's go take a look at one of the spreadsheets here. Here you go. Yes, here you go. So do we see that in one of those three tables here that I display for you? I asked you to write the n, okay? I asked you also to write the equation, right? And I asked you to write the R square, right? So here you go. Those two values combined are the real way of measuring, of determining quantitatively how close your mathematical model is to real life. You have to take into account those two values, the number of data points plus the R square, okay? You may have the same R square for two different sets of data. One is 10 data points and the other one is 8. You may have it. It doesn't mean that they have the same confidence level. No, it doesn't mean. Because in one set of data, you have more data points than the other. That's where the confidence level comes into play. Okay, that's where the confidence level comes into play. The confidence level, yes, indeed, is a percentage-wise measure of how close your regression equation is to your data points, okay? And that's where the confidence level comes about, you know? So now we have the confidence level. The confidence level, you know, CL, is something that is a function of both R square and N. And that's a better way of judge how close your regression equation is to your data points, okay? And in order to determine the confidence level, you need a table, the table that I upload for you there, out there, okay? This, you know, this table here requires very, you know, complicated calculations. It's not easy to come up with this table that you see here. If you look in the internet, you're going to see table. Usually you're going to see this type of table that has only 3 confidence levels. And 90%, I don't have 90% here, 95% and 99%. Okay. Usually you're going to see that in the internet. I put more stuff here because I wanted to get a better reading of my data. Okay. So what are the possible values of R square? You know, possible values of R square. What possible values of R square are 0, 0, and 1 equal. So that's the range of values of R square that you have. There is another one, another statistical value that is related to the determination coefficient. It's called the correlation coefficient. The correlation coefficient is capital R, is the square root of R square. The correlation coefficient, you know, and by the way, it's equal, right? There must be an equal here. It's going to be, the correlation coefficient is going to be -1 to 1, okay? If you take statistics. But I like to use the R square. Why do I like to use the R square? Because Excel calculates the R square, not the R. I don't know why, you know. But when Bill Gates decided to write that software, they decided to calculate R square, not R. That's one that you see most of the time in statistical books, the correlation coefficient versus, you know, determination coefficient. The correlation coefficient versus determination. Okay, so that's the range of values of R square, and that's the range of values of R. In the case of CL, CL has the same range as R square, from 0 to 1. Okay, it's going to be from 0. And don't forget, there must be an equality there as well. Or, you know, from 0%, right, to 100%. Make sense? Okay. That's the background information that you have to know about this lab. R squared varies from 0 to 1, CL varies from 0 to 1 as well, or 0% to 100%. The N is going to be as many data as you want. It's going to be always greater than 0. It's going to be an integer. Now, N is an integer, greater than 1, right? Greater than 1, because you can never have a graph. It's just one data point there. And having said that, I want you to take a close look at this table. This table is not difficult to figure out. It might look complicated because it has a bunch of things in there. But I'm going to summarize the table here in this slide, PowerPoint slide, okay? Let me see if you already have it. Okay, here's the table. The boundaries of my table, right? White paper. Let's change the color. Color, go. I'm gonna put black edges. In this table, you have the following. You have a row for CL. You see the row for CL there? Here you go. Here's the row for CL. We're going to concentrate only on those that are important. In my table, my CL has the following values. 0.95. Remember that I told you that CL varies from 0 to 1? I didn't put 0 here. 0 is all the way to the left in this table. The next one is 0.99. The next one is 0.999, and so on, right? Right? All the way down to 1 minus 10 to minus 7, right? Take a look here. I put 1 minus 10 to minus 7. Instead of people putting a bunch of 9s there, I just put in this notation. Okay, so here you go. We're gonna font upper superscript. Here you go, 10 to minus 7. Remember that I told the boundaries of the CLS, right? It's going to be from 0 in the extreme left to 1 in the extreme right. You know, the number 1 is outside this table. The 0, 2 is outside this table. It's not documented here because there's no need to document the values of CL at 0 and 1. And we're going to get there. I'm going to tell you why. In addition to the CL, we have also a column. And you can see clearly the column that display the value of N. Do you see N there? Okay. N started at where? N started at 3. Okay, here you go. N. For now, you don't have to worry about alphas. You don't have to worry about this df here, that's degree of freedom. Okay. So you go N. I'm gonna write it down. Start at 3, I said, right? 4, 5, 6, 7, 8, right? So on. 6, 7, 8, 9, 10, 30, 39. I went only to 39. If you want to go, if you want, you can go. Okay. You can go to higher numbers. Okay, Crystal is here. I'll give you attendance, Crystal. Crystal. You go. Okay, Crystal. Now, then you have the bulk of the table. You have all those numbers. Here's the bulk of the table. Do you remember that I told you that the confidence level is a function of R squared and N? Remember that? Okay. Oh, I already told you that, this CL here is going to be a function definitely of N. And if I want to know that the value of CL, you must know the value of R squared. So the R squared must be somewhere in the table. Make sense? So the bulk that you see there in the table are the values of R squared. Okay, we call it the critical values of R squared. That's what we call them, the critical values, and called critical for a reason, for a very good reason. I mean, by the same token that we call also critical values of the correlation coefficient, okay? Which is related to the determination coefficient. So here we go. The R squared goes here in the bulk of the table. I'm going to put it very big so you can all understand. Let's see, this one is going to be bold face. I need bigger than that, right? No, even bigger than that. Let's see, can I put 300 size? Yeah, I think I got the size I want. Yeah, and this one. Superscript, here you go. Okay, so here you go. So instead of using that, to calculate the CL is a very complicated function, like I mentioned to you. So instead of having that very complicated function for you to calculate, you just use a table, okay? Just use a table. So here you go. CL here and N here. To find the CL, you're going to need the R squared, and the R squared is also values of R squared of the critical values of R squared are in the body of the table, okay? Most of the table is made of R squared values. Make sense? If you want to calculate, if you want, so let's see, example, let's do an example here so you can learn how to use this table, okay? Example. Suppose you have that you plotted 10 data points. 10 data points in your graph. N equal to 10. And found an R squared I'm going to give you a very simple 10 data points lies right here in this row. Okay. And suppose that we found, oh gosh, see that. And we found an R squared that's equal to this value, 0.863701. 0.86701. Okay. The question is, what is the CL, the confidence level of your regression equation? Okay. And then I'm going to walk you through solution, right? Steps, right? 1, draw a horizontal box, right? Starting at n equal to 10 across table, right? The CL table that I gave to you, CL table that I gave you. Step by step, right? So here you go. CL 10, CL 10, n equal to 10, right? Right in here. In the next step, okay, next, we see within this row, find the R square value. Find the R square values in this row. Within this row. Step by step. Here you go. So we are not going to use n equal to 9. You're not going to use n equal to 11. You're going to use n equal to 10. Okay, you were lucky enough that your R square coincided with one of those values here in your table in this specific problem. See that? You know, then after you find the R square values in this row, move upwards until you intersect the CL row, okay? From this R square, no? From this R square value, move upwards until you intersect the CL row. Here you go. So let's see. We are right in here. We're gonna move upwards. Here is the CL row. What's the value we are reading? At this top, at this value, see? CL right in here. What's the value you're reading? 1 minus 10 to minus 4. Okay? That's how you.
So, Professor, what if your R squared value is perfectly in between two of the values? So instead of 0.863701 or 0.922.853, it's 0.893277. So the perfect average between two of them. Which CL value would you then pick?
Well, I'm gonna cover that soon. Okay, so hang in there.
Okay, thank you.
Hold it there. Okay, so you have a very good point. Okay, in real life, when you perform an experiment, you know, you're never gonna get those critical values of R squared in real life. But let's finish this problem first, right? Let's finish this example first. What's the CL of that? The CL of that is going to be, you know, using my table, right? You can see that the CL value is 1 minus 10 to minus 4, right? Which is 99.99%, I guess, right? Make sense, right? Okay, so here you go. 1 minus 10 to minus 4. You multiply that, yeah, it's 99.99% that, right? I think so, 99, yeah, 0.99% with 2 decimal places there. So the next question, right, is what if your R squared is none of those values? You know, each of those R squares here are critical values. That's why you know, they coincide exactly with the CLs that I documented here in the table. Okay. So what if they, you know, fall somewhere in between? What do? You don't take the average. Okay, you don't take the average because think what this function for the CL is kind of a complicated function and it's not necessarily linear. Okay. So in my labs, what do? You don't take the average. You just report the bounds of your CL. Okay. And again, that's what you are gonna get in real life. So let's go here. In real life, okay, in the above example, the R square was exactly equal to the critical value in my table, right? However, in real life, you never get anything like that. Never get anything like that. Instead, you always find a value that is between the critical values. Okay, and most likely, you know, the student, which was the student that made that question? What's her name? The student
It's me, Meng
yeah.
Zhu.
Meng Zhu, yeah. So you notice, right, that whatever R squared that you're getting there in your table is not matching any of those R squared that's here in this table, right? Whatever R squared that you got in your experiment, right, in your Excel spreadsheet, doesn't match in your graph, doesn't match any of those square R squared that you have here, right? So in real life, it's gonna be, you know, almost impossible to get the exact number that you have here. Okay. There was just one instance that I had a group of students that got it exactly, and I have been doing that for years already, since 2003. You know, thousands of lab reports, and just one case that I had a situation like that, that the student got R squared that coincided with one of those numbers that were in my table. Okay, so what do you do? That's why, you know, I came up with CL min and CL max. A better interpretation for that's not mean, but it's the lower bound of the CL and upper bound of the CL, right? So let's say now let's go to another example. Another example, right? You still have n equal to 10. But your R square is not this one here. Let's do your R square is going to be, I'm going to get, let's say 0.84. Let's say you got 0.84. Yeah. R square, you got 0.84 instead. The two questions, you know, first question, can you determine the exact CL from my table? That's the first question. The exact value of the CL from my table. If you can't, what do you do? What do you do, right? So let's go. 0.84, n equal to 10, 0.84. You go. N equal to 10. Do you have 0.84 exactly here? No, you do not have 0.84 exactly here. Your data, your R square falls somewhere between those two values, okay? It falls somewhere here between those two values. According to my table, you cannot state explicitly, you know, perfectly, accurately, what's the value of the CL. But you can state that my actual CL falls anywhere between 1 minus 10 to minus 3 and 1 minus 10 to minus 4. Make sense? Okay? Lower and upper bounds. Okay? So that's what you do in my labs. That's what you do in my labs. Okay? You're going to, in this specific case, you report. So let's say the R square was 0.84, right? N was 10. The equation was whatever. What do we report here? You report this way. You will have to report the exact number. How do you do that? You type the equal sign. 1 minus 10 to minus 4, right? 1 minus 10 to minus 4. No, it's 1 minus 10 to minus 3, sorry. 1 minus 10 to minus 3. And the other is 1 minus 10 to minus 4. Make sure you type an equation there with the equal sign, so it can do the math for you. I'm going to correct that stuff using a software, okay? that I wrote for this specific means. So let me see. Daniel has a question, right? Oh yeah, what's the R square was greater than the last column? That's a special case, okay, Daniel? What is, yeah, we're gonna cover that too. And the other question that you should ask as well, Daniel, what if the R square is less than that leftmost value, right? Right? You're asking me, what if the R square is greater than any of those values here, right? How do you, what if your R square falls outside to the right of this table? This one is not 1, by the way, okay? This one is not 1, by the way, okay? It's a number very close to 1. We see here? It just happened that I ran out of decimal places and I couldn't write down the exact number, okay? So Daniel is asking, what if the R square is a number that falls to the right, right? To the extreme right of the table. And then you have to ask yourself too, what is the CL value if your R square falls to the left of those values, right? Those are special cases of the table. Those are special cases of the table. So it's 105 right now. Let's take a little break, right? And then I'll answer your question, okay, Daniel? Lawrence, okay. Okay, Lawrence, I'm gonna give you an attendance here, and let's take a 15-minute break. Starting to get Thursday. Can you go back to the last example, please? Sure, I will. Let me just give attendance here to Lawrence. You go, Lawrence. Do you have a group, Lawrence? Doesn't look like you have a group, huh? Okay, we'll take care of that. And you want the notes, right? Here you go. Okay, Jennifer, here you go. That's what you want? This previous one? You will need to be using that table over and over again, okay? This is a simple example that you're lucky enough you got exactly this number, right? But in real life, you don't. In real life, yeah, we'll talk about that. Hang in there, Lawrence. We'll talk about that after the break. You know, something like that doesn't happen in real life. Okay. Every experiment I have done, you know, just thousands of experiments I have done. Just one group of my students got something that is exactly that R square value that was in the table. Just not even exactly equal, just a little bit off, you know, from the exact value. I remember that. It was not even the same value there. I put all sorts of decimal places to make sure something like that wouldn't happen. Okay, 107 right now. Can I go down, Jennifer? So break till 1:22 p.m. It's starting to get very hot here in my house. I become very uncomfortable. I'm going to turn on the air conditioning, right? And in 15 minutes, we see each other. We talk again. In this meantime, start practicing how to use that table. Start practicing, you know, filling up your spreadsheet, okay? And we'll talk about that soon. I'm going to stop sharing here. And I'll see you in I'm back. 15 minutes go by quickly, right? So here you go. Okay, so here you go. So here you go. So here you go. For this case, right? 10 data points, R squared equal to 84. Can you determine the exact CL from my table? No, the answer is no. Not the exact value. Not the exact value. Okay, what you can do? So what you can do? You can, what can you do? What can you do? You can report the upper and lower bounds of your CL. Okay. And what we found out, I type it here, right? 1 times 10 to minus 3. No? The lower, let's put the lower and upper bounds of your CL. In this case, 1 minus 10 to minus 3. Oops. Oops. And 1 minus 10 to minus 4 respectively. Okay. And when you report, while you are reporting that, just a word of caution, okay? Make sure you type exactly the way I typed. Put an equal sign, 1 minus 10 to whatever, right? Similarly here. And when you do that, Excel is going to calculate the value numerically for you. I frequently see students making this mistake. They don't put an equal sign here. And because they don't put an equal sign, Excel treats this value here as though it is a text. And my software cannot correct it. My software corrects only numbers. It doesn't correct text. That's one mistake that I see from my students. Another mistake that I see from my students, they don't do the 1 minus 10 to minus 3. They just display the 10 to minus 3 there, okay? This is not the CL. This is not the CL. This is something else. This is the alpha value, okay? But you shouldn't worry about alpha. You should worry about CL. And N and R squared. Okay, so how are we doing there? 32 students. Now, so let's see. Lawrence, right? You want to join Kenny's group? Kenny's group is group 1. Let me see. Yeah, every group has 40 students. Okay, so I will let you join their group. Well, yeah, ideally, we should have no more than 40 students. But because every group has already 40 students, I'm going to let you join them, okay? Today is the 16th. Here you go. I'm going to insert you. Now I want this one here. Oh, freeze. Okay, good. Now one of you asked me, what if the R square falls outside, right? Outside my table. We're gonna get there. Let me just reorganize. Group number. Level name. Okay, we go. Toby, Florence, good. Now we have another example. And it's possible, something like that, that one of you mentioned is possible. Okay. So before we move into that, right? Make sure you type these numbers in the cell following way. Equal, let's say equal. I'm gonna put between quotes, okay? Equal, right? 10 minus 3, like that. That's how you're supposed to type in the Excel spreadsheet. Equal 10. Oh, don't forget to put the equal sign. You must put the equal sign there, otherwise Excel is not gonna calculate those values. Okay. Example 1, let's put here. Example 1, example 2. Now we're gonna do it in a different way. Here you go. Example 3, another example. What if your data is so good, but so good, that your R² is more than this value right in here? Okay, so let's say R² is 0.90. I'm gonna put 0.99. .99. I have seen that. It happens, especially in the physics 38 experiments. The physics 38 experiments, we get very high confidence levels, you know. Let's see, we have some question here. It's just you cannot hear. Let me see. Okay, everybody else can hear. Toby cannot hear me, right? But everybody else can. Okay, good. So you might have a problem there with your well, he can't hear me, right? So so let me just reply to Toby. Hi, Toby. May have a problem with your speaker. Oh, Toby looks like he got out. Okay. Yeah, we're gonna get there, Daniel. We're gonna get there. And you're assuming n equal to 10, right? Right, Daniel? Okay. Oh, n equal to 8. Okay. Let me see. So n equal to 8. N equal to 8. Okay, if you're having 0.99, so 0.99 is between those two values, right? Now, if you have 0.999, so 0.99 is definitely outside the table, right? So what do you do? Okay, it's very similar to this other one, this other example that I'm doing. Okay, so let's do it together. I'm doing for n equal to 10, and R² equal to 0.99 is outside the table. What do you report? Well, you do report that the lower bound is 1 minus 10 to minus 7. Yeah, you do report. The problem is the upper bound. Problem is the upper bound, right? How do you report on the upper bound? Definitely the lower bound is going to be solution. Here you go. Solution. Definitely the lower bound will be 1 minus 10 to minus what? Minus 7, right? I need that. Oh gosh, that's not this one I want this one. Definitely, you have to report that. 10 to minus 7. Right? But what about the upper bound? Well, the upper bound, you do not know if maybe it's 1 minus 10 to minus 8, maybe. Or maybe it's not 1 minus 10 to minus 8, maybe it's 1 minus 10 to minus 9. But you do not know if it is either numbers. My table doesn't have enough resolution to tell you if it's those numbers. Okay, so what do you report? In this type of situation, you report the upper bound as being the maximum value of CL, which is 1 or 100%. Make sense? Okay, that's what you do in this case. And don't forget, make sure, right? Make sure you type these numbers in the cell in the following way. The first one, you type like that. And the second one, you don't have any formulas. All you have to do is to type the number 1 there inside the cell, right? Don't put the quotes. Don't put the quotes. Don't put the quotes, okay? And then you have the other way around, right, Daniel? You have the case in which the numbers are to the left of the R square, of the leftmost R square, right? So what if, I'm doing everything for n equal to 10, right? I'm gonna copy and paste here, but now your R squared is no longer 99. R squared is gonna be, 0.3. It's gonna be 0.3. Definitely the upper bound is going to be what? 0.95%, right? 0.95%. But the lower bound, you cannot say it's 0.9. You cannot say it's 0.8. You cannot say it's 80%. You cannot say it's 90%. My table doesn't tell you. So the only reasonable answer that you can give is 0, right?
0.
That's it. If you want to know exactly your CL, then you have to go through that big equation for CL that you have to calculate it. And this equation is not easy, folks. I went through that, okay? I know how to calculate the CL using the actual equation, but it's not, it's not an easy task, okay? Even with Excel, by the way, even with Excel. The function is really, it's really complicated, the function that calculates CL. That's why we use tables. That's why we use those tables. So it's 1:40. We have 20 more minutes to go. Let me see. This thing here is gonna go somewhere else. Is that clear? I frequently find my students reporting the wrong value, okay? What the students usually report. I have lots of experience with that. So what mistakes the students usually make? Okay? What mistakes students usually make? Okay. They do not. That's one of them. I see that all the time. They do not report the lower and upper bound of the CL. Instead, they report the lower and upper bound of R square. That's what they do. I see that over and over again. So if your R square lies anywhere here, instead of reporting those two values, the students in general, what they do, they report this as the lower value for the CL, when in reality it's not a CL, this is an R square, and report this one as the upper bound. Okay. When I see those numbers, it's obvious because I made my CL with those predictable values, right? 9.
Okay. That's one mistake that they make. And then I already displayed another mistake, right? Okay. I pause it here momentarily. The other mistakes, right? So they do not type the numbers properly. They type the numbers. Students type the numbers. They do not report, instead they type the numbers without the equal sign. Type the alpha values in the table, on the table, instead the CL. Okay. So now you can finish, right? Now you can finish your report. So those are the several mistakes that I see in there. In the lab. And I think that's all I wanted to cover with you. Okay, let's finish this spreadsheet. We should have like 18 minutes to do that. I do not know if you have already finished. Let me know. If you haven't, let's work together to finish, right? Graph, regression equation, right? And here you go. Here's the regression equation. Fill the values for R squared, and you gotta report the coefficient, the units for the coefficient, right? And as that's the last thing that you do, the CL, because that's the most difficult one, right? The most difficult we usually leave for the last one. Once you get the graph, you fill up those values, slope, intercept, so you can look at the percentage difference. Okay. Just as a caution here, the unit for the percentage difference is just the percent sign, okay? I'm giving you that. It's just like what we say, percentage difference, unit is the percentage. So make sure you type in there, because I take lots of points out of the units. This lab report, this first lab report is due the 20th. Yeah, the 20th. Monday is due next Monday. The 20th, okay? June the 20th. Let's go through one by one and see how you folks are doing. All right, one more here. Toby, did you finish with everything there? The spreadsheet? Is Toby there?
Toby can't hear you.
Oh, that's not good. Okay, so let's see. Let me send a message to Toby. Oh, but he logged off too. Yeah, he cannot hear me, but he cannot receive a message either. Okay. So let me put a star here. And Pedro, did you finish, Pedro? Pedro cannot hear me either. Pedro. Yeah, Pedro is not. Oh, Pedro Flores. Yeah, Pedro is here.
Hello?
Yeah, can you hear me?
Yeah, I'm here.
Uh-huh.
Yeah. Sorry, can you repeat the question?
Okay, so some people are having problems with the. Let's see. Let me check my mic. Hang in there. Zach is having. Can you hear me, Pedro? Well, can you hear me well?
Yeah, I can hear you.
Okay. Who else is having problems? Toby is no longer online. I don't see him. Okay, Amalia can hear me. Zach is having a problem. Anybody else? Okay. Yeah, I can hear you. I can hear you. Okay. Apparently most of you can hear me well. Okay. So if you're having any problems, try to log off and log in back. Okay. So here you go.
Yeah, I think your audio is fine, Professor. I think it's a connection problem.
Yeah. Okay. Must be connection, internet connection to yours, right? So did you finish the spreadsheet, Pedro?
Yeah, sort of. Me and Nolan finished the spreadsheet, but we're having we got a big % error.
Big percentage error. Okay,
Yeah.
you're group number 1. Let's check. Let's check what's the problem here. Group number 1. Sometimes it's the data that. For which graph are you getting a big percentage error? For which graph? First, second,
The
or
second
third?
graph.
The second graph. Okay, so let's plot together. 1 and 2, right? It's possible that it just don't have a good data there. Linear display, or it's also possible that you go. That's the slope, right? 3249. Yeah, you're right. You're getting a large percentage difference, huh? 3249. You're getting 19%.
Yeah, that's what we're getting.
Yeah. Well, if you're not at fault because I provide you the data, right? If it were if you had done this experiment, I would tell my students to do it again, to do it all over again, because this experiment gives us lots of good results. So you're not going to be punished for that. You're not going to be, okay? So it's okay. 19% for this experiment. Yeah, 19% for this experiment is high. So unfortunately, the students who generated this data, apparently they didn't do a good job, okay? So he goes, anybody else? So let's see. So if you don't, yeah, so you said you finished, right, Lawrence? Are you done there, Lawrence? Make sure you practice CL. There will be a question about CL in the exam. Are you there, Lawrence? Yeah, Lawrence, I don't see Lawrence listed. I'm gonna put a star here. Kenny, are you done? Oh man, Kenny is not here either. Okay. Nolan is here, right?
Yeah, I'm done.
You finished, right? Okay, if you wanna go, you can go.
Cool.
Let's
Thank
see.
you.
Welcome. So 10 more minutes to go. Harun, are you done, Harun?
Yeah.
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 You got CL, everything. Okay, if you wanna go, you can go. Musa, are you done?
Yes.
Yes.
Yeah.
Okay. Okay. So any questions? Do you have any questions, Musa?
No. No, I don't have any questions.
Okay. And Daniel?
Oh yeah, we are done.
You're done. Okay. Do you understand everything? You're seeing CL for the first time, I presume, right?
Yes, sir.
Yeah. Okay. So it's a very the CL is an interesting statistical parameter that people haven't paid much attention to, but it's a very important one, by the way. Dave,
Yeah.
Okay, good. Zachary Blue. Are you there, Zachary?
I'm not finished.
You said you are finished?
I'm not finished.
Oh, not finished. Okay. Do you have any questions? Do you have any doubts? What's going on there?
I'm planning on completing it later.
Huh.
So I was hoping that maybe the recordings, I might be aided by the recordings.
Okay. Okay, I will upload it this weekend. So here you go. Elena,
Okay, I appreciate that.
welcome. Hi, Elena.
Yeah, I'm almost done.
Almost done. Okay, almost. Okay. Any questions about the CL or anything else?
No.
Are you getting good percentage differences?
Yes.
There? Usually we get less than 10%. You know, group
Yeah,
one.
they're less than 10.
Yeah, maybe even less than 5 for this experiment because this simple pendulum works very well. Luis Crystal.
No, I'm not done.
Okay.
I'm going to work on it this weekend.
Okay, but did you understand the CL?
Yeah.
Okay, not done. David Maes, right? Let me know if I'm pronouncing correctly. Dave is here. Not yet. Okay. Okay, not. Okay, I can put not here as well. Who else is coming? Toby. Here you go. Robert Faust, are you done? Let's see. Robert, can you hear me, Robert? Want to know if you're done or not? If you have any questions. Okay, I'm gonna put a star here, not answering. Next, Daniel Frady.
I'm almost done, but I have a question about the logs and the units for those, the log graph.
Yeah. The units for the log already put that for you. Okay. It's a unitless unit.
So I can put that for the.
Yeah. You put it between parentheses, right? In the graph, you put between parentheses 1.
1, so that means the units are 1 for the other box. Okay, thank you.
Yeah, 1 means unitless unit. The radian, for instance, the radian is not, which is a way to measure angles, right? The radians in reality is a unitless unit. You just call it radians to distinguish it from degrees, okay? So strictly speaking, radians is not a unit at all. When you are doing your math, if you see radians in there, you can interpret the radians as the number 1. Okay. Now next, you're not done, right, Daniel? Let's see here.
Professor, I have a question. This is Toby, by the way. So I can do. So I'm not done with the lab. I'm almost done. But what's it called? How many? Is it just one report that the whole group sends?
Can you type your question in the chat? I didn't. You're coming very low here, so and I will reply to you in the chat box. Okay, send me a text chat message, private chat message. I'll reply back to you. I can hardly hear you. Okay. So here you go, Olivia.
I'm pretty much done, but I have a question.
Yeah, what's that?
For my first graph for the T average versus L, I'm getting for the coefficient 18.7, but I know I should get 1.87 because the theoretical is 2. And I know that's just like a unit or sig fig mistake, but I don't know where I made the mistake.
Okay, so you're group number 4, right?
Yeah.
Which graph you said?
For the first one.
The first graph. Okay, so you plot the first graph, the T average. You go with this one, right? Insert. Oh man, this is a bad. Yeah, that's see. This data is all over the place. Let me see here. No, wait a minute. Doesn't look like I plotted right. T average, L, insert. Yeah, okay, good. You got something like that?
Yeah.
Okay, good. So now you're going to fit. Remember, you're going to do a power fit here. You're not going to do a linear fit. Do you do a power fit here?
Yeah, I did.
Okay, power fit. Okay, and then you're going to display equation chart. I'm getting 1.87. 1.87. Is that what you got?
I got 18.7, but maybe I'll just do it again.
Yeah, maybe you made
I
a
got the
mistake
same
there.
graph.
Huh?
I got the same graph as that. Just
Yeah, but I'm getting 1.87. I do not know why you got 18.7. I do not know. There might be a factor of 10 in there that you missed. Did you change your data somehow? Maybe you changed your data somehow. You didn't know. You know, those are possibilities. Okay.
okay. Yeah, I'll just do it again. Thank you.
Okay. Now.
Hey, Professor.
Yeah. Who's that?
Yeah. Can we leave if you've already?
Yeah. It's gonna. Yeah. You can leave. It's already 3 minutes, right? 3 minutes to go. Let's see. Let me go as quick as I can here. Attend that. 3 minutes to go. Olivia is still working on that. Let's see. Are you okay, Lou? Do you have any questions?
No.
Yeah, I'm okay.
You're okay. Okay. Did you finish everything? You know.
No, I'm not done. I still need to work on it, but I'm
Okay.
doing okay with it.
Okay. Okay. Good. Yeah. Okay. Whoever is leaving. Okay. Have a good day. Let's see. Amalia, Gail.
I did not finish it yet. I still have work to do on it.
Okay. Good. Do you have any questions? Do you?
No, Professor. I
Okay.
just need to work on it some more.
Okay.
Have a good day.
You too. Tiffany.
I'm not yet done.
Not done yet. Okay. If you have any questions, just let me know. I'll be staying here for office hours, right? Anthony?
Not yet. We're almost done though.
Almost done. Okay. Any questions about the CL? Do you understand how to get it? How to get this
Yeah.
result? Okay. Good. Shah?
Not done. I'm just stuck with the CL. I couldn't understand it actually.
Okay. You couldn't understand what?
So if I have a R square value, if I have a R square value of 0.9992, and then what is my lower and upper bound for the CL?
Okay. Okay. So let's see. Let's go to the table, right? Is n 10, right? N equal to 10, right? So your R square is 0.99, you said, right?
0.992.
Okay, so your R square lies right in here in this region, outside the
Isn't-
table, right?
Isn't
Yes.
that N8?
No, it's not. No, is it an 8 or 10? Let me see
There's
here.
only 8 measurements.
Only 8 measurements. Let's see. Oh yeah, thank you. Yeah, it's 8 measurements. So let's go 8 here. So you're getting 0.99. What else?
92.
9992. Okay, so definitely it's falling outside the table. Okay.
Okay, so let's say equal to 1.
Well, the lower bound is 10 to
That
minus, right? It's
Okay,
this one
yes,
here. The
yes.
upper bound is 1. Okay.
Oh, perfect. I got it. Thank you.
So it is the same case as example. Which example? Example number 3. The same case as example number 3.
Got it. Thank you.
Okay. Sure. Okay. Finishing. Daniel Yang. Are you okay? Pretty much done. Okay. If you want to go, do you have any questions, Daniel? Okay. Good. Ryan McNeil. Not sure if it's right. I have a lot. Okay. If you want to stay for the office hours, I can help you out. Okay. And Claire.
I'm not finished yet. I actually had a question about the recordings.
Yeah.
And I kept checking on your channel, but I was just wondering when you would like upload the recordings.
Yeah, I'm gonna do that
this
this weekend.
Okay, awesome.
Okay, maybe tomorrow. Okay. So here you go, George Risk.
Yeah, Professor, I'm almost done with it.
Almost done. Okay, any questions?
No,
Okay,
thank you. You have a good day.
Jennifer, you too. Jennifer Ramirez. I'm done. You're done. Okay, good. Any questions, Jennifer? Okay. So if you want to go, you can go. Next, Noah Raymond.
All finished up, Professor.
What did you say?
Oh, all finished up.
I'll finish that. Okay, if you want to go, you can go. Unless you
Have a
want
good
to
day.
stay for any questions. Natalie Santiago.
I'm done, Professor.
Done. Any questions?
No, I'm okay. Thank you.
Okay, good. Mengshu.
Yep, all finished, Professor. Should be
Finished.
done. Just a quick question. In terms of there's a units for the final box, and it's a percent difference. I mean, do you want us to leave it blank or just write percent difference unit list?
Let me see. I didn't quite understand your question. What's your question?
I'm just saying there's a third box for the delta unit of the delta, right?
Yeah.
And if you look at the calculation, it's a percent difference. So
yeah,
there's technically no units, but we can just put percent difference there, right?
Yeah, you put the percentage because
Okay.
you're multiplying by 100, right? When you multiply by
Yeah,
100, it's no longer unitless, right?
Yeah. Mhm.
Okay, so you
Okay,
do
sounds
put.
good.
Okay,
Sounds good. All right, take care, Professor.
welcome. Next, Sarina. Let's see, Sarina. Okay, not yet, almost. Okay, any questions, Sarina? No? No? Thank you. No, Alexis?
Yeah, I'm done. I'll be uploading later.
Okay, you're done. Okay, if you want to go. Danis.
Thank you, Professor. Bye.
Bye-bye. Olivia Song.
I'm done too.
You're done too. Any questions, Olivia?
Can I have a code for the enlarged class?
You want what?
Code to enlarge the class?
Oh, okay. Yeah. I can give you a code. Let me see here. Nathan first, and then is Nathan there? Nathan doesn't have a group. Nathan Silva. Yeah, you're there. You don't have a group, Nathan. But anyway, you missed the lab, right? Yeah. Okay. Who is that? Who is Don Zoom user?
Hello, Professor.
Yeah, who is that?
It's Kenny. You called me, but I was eating a sandwich. Sorry.
Okay, Kenny.
Yeah.
Yeah. Are you done, Kenny?
Yeah, I'm done with the graph.
Okay. Okay, so you can go.
Thank you.
Okay, whoever is done can go, and I think we're done here. And there's this student that needs an add code. Let me get you an add code. It's Olivia, right, Olivia? Olivia, you're trying to get an add code, right?
Yes.
Okay. Let me stop sharing the screen. No. Let's see. Okay, let's stop sharing and black blue. Okay, in your case, Olivia, did you try to add, or what happened?
Sorry?
Did you try to add the course?
No, I was just still on the wait list.
Yeah, because the other shoes were in the waiting list, and they didn't need an add code. So let me get here your, but I'll give you an add code anyway. Okay. Okay, I'm gonna send you through the chat, private chat message, okay?
Okay, thank you.
Olivia Song, please confirm that you got the ad code, permission number, call it the permission number, here you go.
Yeah, I got it. Thank you.
Okay, write it down, don't miss it, don't lose it. Anybody else need any help?
Yeah, Professor, I send you a text.